Good afternoon, and welcome back to this Texas Space Grant Consortium Design Challenge Virtual Showcase for Spring 2021. Our showcase teams will begin shortly. If you have any general questions or issues during the showcase, please contact us at TSGC. Oh, I'm sorry, that's a typo there. It should be designchallenge@tsgc.utexas.edu. So welcome to all the teams. There is our email address at the bottom left, designchallenge@tsgc.utexas.edu. We have 10 team video presentations this afternoon. If you missed any of yesterday's presentations, they are streaming on YouTube. So welcome to all our YouTube viewers, as well as all the students here on the Zoom webinar. We will have 3 sessions with 2 10-minute breaks. Team video presentations are 10 minutes, and then they'll have a 10-minute question and answer session. During the Q&A, please ask your questions at slido.com and use the code TSGC to ask your questions or to see other people's questions and upvote them. We're not using the question and answer session on Zoom or looking at the comments on YouTube. We're doing it all in one place on slido.com. Here is our schedule for today, Wednesday, April 21st. We have 4 teams in our first session: University of Houston, UT Tyler, Lone Star College, and San Jacinto College. In session 2, we have Texas A&M Kingsville, UT Rio Grande Valley, and Lamar University. And in session 3, UT Tyler, UT Austin, and Texas A&M. Again, if you have any general questions, please email us at designchallenge@tsgc.utexas.edu. I am Tim Urban, the director of the Texas Space Grant Consortium. With me online are Talia Jurgens and Angelica Kurzinga, and we can certainly help you if you have any questions. Our first team is from the University of Houston, Team Bon Mi, and they have been working on the NASA Suits project.
Hi everyone, we are Team Bon Mi from the University of Houston. Dr. Dunn and Dr. Chang are our mentor and advisor. The project couldn't have been a success without their support and guidance. My name is Ngọc Nguyen.
I'm Ashwin Matthews.
I'm Nancy Nguyen.
And I'm Almira Shara.
Today, we take turn to talk about AR overview, our design with testing and results, and we end with future work and conclusion.
In NASA Suits, the primary goal of augmented reality or AR system is to assist astronauts with EVA responsibility in a way that when they're on a lunar surface, they can use their time proficiently. The 3 tasks of navigation, EVA system, state, and geology sampling were given to us by NASA Suits. For the navigation part of the design, the AR device must have the ability to navigate the user from one point to another and to the designated geology sampling location. For the EVA system state, the device must have the ability to interact with the designated suit telemetry stream and display vitals. And finally, for the geology sampling, the device must have the ability to help the user with science sampling and note-taking. In this table on the right-hand side, list of tasks for analog testing are shown.
So before we walk through the program, we'd just like to introduce some methodology used in creating it. The first consideration is interaction cost, which is defined as the sum of all mental and physical efforts used to perform a task. In this image, the user's mental efforts involve processing the GPS navigation and applying those directions they're driving. and the physical efforts involve operating the car and clicking through the GPS system with their hands. Generally, a lower interaction cost is desired. The next consideration is something called cognitive load. Look at the top and bottom lines of text. If I were to show you both lines and ask you to replicate them from memory, you'd probably have more success replicating the bottom line. This is because your brain processes information in separate groups of information called chunks. In the bottom line, your brain groups each acronym into a single chunk like IBM or USA, but the top line, however, features randomly placed letters of differing length, which forces your brain to treat each letter as a separate chunk. Cognitive load theory tells us that the brain can only handle so many chunks of information at once, and the lower that amount, the better. The last consideration is seamless task switching. When you operate your smartphone, you're very easily able to switch applications or tasks through the app browser. Similarly, we want our AR system to exhibit the same qualities when switching from an operation such as navigation to another such as geology sampling. Overall, we'll keep these three theories in mind when showcasing our AR UI.
The first step in the design process is the ideation or brainstorming phase. In this phase, we took requirements from the suit's design challenge that we mentioned earlier and created a how might we question. The how might we question that we use to guide our design is how might we assist an untrained astronaut to safely complete all of the missions without feeling overwhelmed. After creating the how might we question, we brainstormed possible solutions that we wanted to include in our design. After the ideation phase was completed, we then created a user flow map that shows the steps a user could take to complete an EVA. Afterwards, we created low-fidelity versions of each screen in our wireframe. Using these wireframes, we created each screen of the user flowchart in Unity. Lastly, we deployed the Unity build into the HoloLens 2 for testing.
Our app is programmed to start as a home hub in which a user can choose to go through tutorials or solve from specific tasks. These features allow seamless task switching as a user can go back to the home hub at any time. What is showing in this video is what the user would see inside the HoloLens. As you can see, the tutorials are very simple and easy to follow so that anyone can learn how to use this program regardless of their level of experience. Moving on to the first task, the picture here shows the UAA physical hardware that a user would have to work with. There are 15 steps that they have to go through, and in order to not overwhelm them, we break down the instructions in different frames, and we also position the instruction boxes so that they are visible but not blocking the physical UAA. After the task is confirmed to be complete, the program will automatically navigate them to the next site for the second task. The second task is geology sampling. The program had to provide cue cards while allowing the user to take notes at the same time. Our team tried out different note-taking methods, and we found out that using voice command to take picture of the samples is a method with the lowest interaction cost, which will be shown in this video.
Take photo.
So in addition to that, the digital cue cards with tools info will be available at any time.
Moving on, our navigation system is shown here, and it intuitively guides the user to their destination using a glowing line and green arrow to follow from their location to the target. The target is encompassed by a large green circle and distance indicator telling the user how far they are away from their destination. When they reach the target, this circle turns bright purple, communicating to the user that they've arrived. Now on the left hand of the slide, we have our view of the final task that the user gets to perform, where they're instructed to retrieve rock samples at their destination and confirm retrieval using the task complete button in the bottom right-hand corner. Throughout the entire experience, the user always sees elements showing them the status of the spacesuit, which is called the system state. To point out some of these elements, we have the vitals listed at the top of the user's view at all times. This includes items like oxygen levels and the battery time that they have remaining. During movement, however, some of these less important items disappear in an effort to reduce cognitive load. They return again when standing still. Now, if a vital is out of the expected range, you'll notice an emergency notice appears in the center of the user screen and disappears when the anomaly is either resolved or goes away. Now, finally, if the user wants to exit the experience at any time, they click the Return Home button at the bottom left-hand side of the screen.
This semester, the team has managed to conduct 2 separate HEDL testing. A total of 16 volunteers with different level of AR and VR experience participated. For the first HEDL testing, the focus was more towards the visibility of the app. For the second HEDL testing, 3 versions of the app were tested, and the focus was on both visibility and the usability. Before, during, and after each testing, the COVID-19 restrictions were followed. During the testing, the test subject was verbally guided through the experience and was asked to verbally express any trouble they had during testing, and those feedbacks was noted by the team. The video of the whole process for each test subject was also recorded by one of the team members. And finally, at the end of the testing, the test subject was asked to complete the feedback survey.
Overall, users indicated that our UI was intuitive and that the UI elements were easy to read. This can be seen in our post-testing survey scores as shown in the table to the right. Another key takeaway that we noticed during HEDL testing was that voice commands were highly preferred over gesture commands for the note-taking portion in the geology sampling task. For example, when taking a photo, users expressed that pressing a button to take a photo was very cumbersome. Meanwhile, saying a command like take photo to take a photo was easier for the test subjects. Lastly, we noticed that UI elements set at a distance of 0.15 meters away from the camera in the Z direction allowed for a UI element to be both readable and within reach of the user. The results and feedback from the HEDL testing allowed us to make improvements on our UI.
Even though our app has been built into the HoloLens and sent to Suits, there are still areas that can be further developed. These include cross-user communication, slope detection, and updated cue cards. Our design is able to assist all the tasks for analog testing, and improving those areas will be greatly helpful for actual future lunar missions like Artemis. As Suits and THGC programs are coming to an end, there are a few more deliverables that we have to work on, including analog testing, exit pitch, white paper, and an outreach report. The 2 pictures here are from the outreach event that we did, in which we showed a student how to make a quick bowling game in Unity and provided them with STEM resources from NASA.
Just to wrap things up, the Suits project gave us the unique opportunity to be both designers and developers of this AR program. In semester 1, our design phase, we focused solely on creating effective solutions for the challenge assigned to us. But in this semester, we had to shift our mindsets to actually coding those designs into a functional AR program. With this transition came some great takeaways for us and possibly some future teams to look out for. To start, we learned about the wonderful capabilities of the HoloLens, but more importantly, the limitations of the hardware as well. For example, the HoloLens screen is much smaller than you'd expect, and with these limitations definitely came some design changes. We also discovered just how important testing was to this process. There were multiple times we coded solutions which we thought were intuitive and easy to pick up, just to learn that wasn't the case when handing it off to a test subject. Only through testing were we able to find that important user feedback and incorporate into our final design to be that much more user-friendly. At the end of the semester, we're happy to say that we found a great stopping point in our program, and we're very thankful to have it selected for on-site testing happening in the following month. We learned a lot these past 2 semesters, and we hope to work on some more fun projects like this in our future careers. Thanks again for joining us, and go Cougs!
All right, team, welcome.
Hello.
So great project.
Thank you.
Audience, go ahead and ask your questions on slido.com. Enter the code TSGC, and you can view and upvote other people's questions as well. I will go to the first question here. It says, did you get an inspiration from virtual reality headsets?
We for our inspirations of all the components that we put in our UI, actually it's from everywhere, we would say. So because we get inspiration from the apps that we use on our phone for navigation specifically, because we all drive. So it draws inspiration directly from Google Maps or any navigation app that we've been using. And while our team member, Nancy, she plays a lot of video games. So that helped us a lot too, in terms of like thinking about where should we start, like which menu should we put in, things like that. So I would say it's not just with the VR headset, it's a little bit everywhere in our daily life usage.
Yeah, I can definitely see the gaming influence on the navigation. That was good. Good. So tell us about the on-site testing you'll be doing in May.
Yes, so for that on-site testing, the SUSE team has planned a whole analog testing procedure in which they plan out really carefully what tasks would need to be done for each at each destination. And it's supposed to be on-site, but is because of COVID. So all the teams would be calling in virtually, but we will be giving direction in real time. It's like we will be able to see the user putting on our headset, starting, and then we will guide them on how to start calibration, how to start on our app. And the way we design our app, the end goal is to make it really intuitive so that we would only need to give very little instruction. So they will be able to just navigate through the app on themselves and be able to do the task that they need to do.
Okay, great. Great to see technology helping technology there.
Yes, yes.
All right, audience, go ahead and ask any other questions you have. Would users risk comfort when wearing this device, the HoloLens that you were using? How was it comfort-wise?
In my experience, because as for me, I've been using this HoloLens a lot, and for the team members too, because we have to constantly put this on. I actually have it with me right now. It's not that healthy, but when you put it on, you definitely feel like putting on a helmet. So in the beginning, some people may feel a little bit of motion sickness if they have to use it for a long time. But after that, it should be fine. And as we did our HITO testing, asking a lot of test subjects, we didn't ask them specific questions about comfort because that would do more with the hardware, with the HoloLens, rather than with our app. We want to concentrate on our app response. But we didn't hear any concern in terms of comfort either. So I would say it may be uncomfortable at first because you're not used to it, but after a couple of use, you'll be really used to it, and everything would seem to be very immersive and easy to use.
Okay, great. So how did you choose your volunteers? Were they other students or family and friends? How did you pick them?
We don't just like pick, we send up a site form for all the students at UH, and we got a lot of response because everyone is interested in how we're going back to the moon, and the AR technology is really fun. So we basically to take whoever signed up first on our form, and because also we can only have for our full test day, and for everyone to be able to go through the full app, we also have to think about the battery life as well. So it's a lot of other time constraints that go into it. So we would love to test as many as possible, but we can only take so many. Yeah.
Okay, good. And so you tested on Earth, obviously.
Yes.
Next question is, would the device work in an isolated environment such as the moon?
Well, so that's really back to the other question. I think the plan for the SUSE teams is that they would definitely make this technology work on the moon, but I'm not sure if they would be using the HoloLens specifically, or if they would have to make their own head-mounted display to use on the moon. Yeah.
Okay. Next question asks again about wearing it. How long would someone wear the wear the device? And do you know if there are any risks from prolonged use?
Oh, that's a great question. I feel like Microsoft will have done some research on this, some intense research on how user, like the long-term effect of it. For specifically for analog testing in the SUSE competition scope, the duration of the test is only an hour. And all of us, along with all the HITO participants that we had, we all like put in the HoloLens around like at least for half an hour, so like 45 minutes into an hour, and we all didn't have any noticeable effect, I would say, out wearing it.
Okay, thank you. So let me ask one final question here for all four of you. So this has been an amazing semester. You've all worked very hard, all the teams, in the midst of COVID and a winter storm, plus your technical challenges. So what were your biggest hurdles getting through this semester?
Oh, if I can start in that one. I think definitely the winter storm and the other remote challenges we had were a big part of it. One that we, I guess, didn't expect initially was that a lot of our coding is done in the Unity platform, just on our computers individually. And that actually has like a preliminary kind of testing center for us to work with so we can try out our programs. But there were major discrepancies between Unity and actually deploying it on the HoloLens. So there were many times that we had to meet together just so people could try out their like individual pieces of the program on the actual hardware. So that was that was definitely something that we had to plan for and make sure that we could meet pretty often to perform.
Yes, I think that was a perfect response. We all had that same problem. I would say though, at first we thought of this project would just allow us to each work on our own computer and that's it. But it turned out we had to meet up a lot and make sure that everything worked perfectly in the UI. And I actually enjoyed the components of this project a lot because it really showed us how like we put our part together and how we can make sure that the whole program runs really smoothly. And also by meeting up, like we were able to give feedback faster as well, and it was a lot more productive when we meet up because all the feedback was like right there. We can go back to our Unity program and fix it right there. So that was nice. But yes, the winter storm definitely put a strain on our time side, trying to meet the deadline, all the GitHub uploads, things like that. Yeah,
it really did. Yeah, I think the most difficult part of it was meeting in person and the winter storm as well. Yeah.
I guess I can go next. I feel like it's been really challenging, especially since we all have a mechanical engineering background, so everything was sort of new. Learning about GitHub, and when we got to the SDR, the software design review, we had to sort of explain terms that we didn't realize we were doing by accident, and we had to sort of label them, like the software engineering terms that we were using. And I guess also we're doing a capstone project aside from this, so just juggling our capstone requirements along with this design challenge has been really challenging, but I think we've been getting through it pretty well.
All right, great. And so, yeah, as mechanical engineers working on software, what's your biggest takeaway from this project?
For me, it's so refreshing because we always been working with hardware and mechanical stuff. So for me, it was really fun to like get on the software side of things and how to see and how it worked together with the headset. It was really fun. But it was definitely, there was a big learning curve for us. But now that I look back at it, I think a lot of the engineering design principles is just like the step is just the same. Like we have to brainstorm, we have to ideate ideas, we have to start making prototypes, and then we have to test the prototype and we have to go back and revise things. It's really similar. It's just now that everything shifts to a digital world. Yeah, that's what I would say. Maybe Ashwin can add more into it.
Yeah, what Nok just mentioned was a big one. Just the process seemed to be like almost really similar to what we were doing for our other capstone project. I think something else we also noticed were just how quickly we were learning, and maybe just being kind of proud of ourselves on that too. I remember at the beginning, we were pretty often just looking up Unity tutorials on YouTube and just checking the documentation almost every single day on just how to do simple things. But by the end, by the day that we actually shipped, we were deploying pretty quickly. We were able to just go into the code, go into C# and mess with our scripts or whatever we need to do pretty easily. So yeah, I think the progress was a big one too.
Excellent. Well, thank you very much, team. Good luck testing in May.
Thank you.
Thanks, Tim. Appreciate it.
Thanks for having me.
All right, our next team is from the University of Texas at Tyler, and it is Team Selene with their initial Mars base.
Hello everyone, we are Team Selene and we are presenting the Martian Aquaponics module prototype. My name is Edgar Reyes, I'm the communications officer. With me today is Aaron Sifilif, the team lead, Kristen Puckett, the treasurer, and Christopher Nobiger, the R&D lead. Now what you see is a quick overview of our presentation today. Many of you may be wondering what our actual topic is for TSDC. We are presenting the initial Mars base. Essentially, we are tasked with designing a base and then looking at a specific module within that base and performing detailed design analysis on it. Now, many of you may be confused and wondering why Mars? Well, NASA has been wondering about Mars and colonizing it for the future for quite some time now. The reason being because of its proximity to Earth, as well as the fact that it has water. Now, as we all know, humans need food, water, air, and shelter to survive. For this system, we will be looking at the food and the shelter. As you can see here on the right image, you can see the fact that we'll be using radiation covering. It will be modular, and the fact that we'll be using geodesic domes in order to distribute the pressure and stresses of the system. You can also locate the fact that the aquaponics module will be within a specific part of the base. I will now be passing off to Aaron to talk more about the aquaponics module.
You may be wondering, what is an aquaponics module or cycle? So aquaponics cycle is basically a garden on top of a fish tank where the fish create waste that is turned into fertilizer for the plants. And in turn, the plants actually filter the water. So the fish provide nutrients for the plants and the plants clean the water, and it's a continuous cycle. Through our research, we were looking up as far as Mars specifications and for a healthy habitat for tilapia and fish. We found that 3 gallons of water per 1 pound of tilapia was feasible for a good living environment and a 1-to-1 ratio for plant to tilapia. This chart here shows some of the water requirements that we found for a healthy living environment for the plants and the fish, as far as the dissolved oxygen, temperature, pH, and ammonia goes. So with this information and with the theoretical equations and calculations that we found, we implemented that into a UI, or a user interface, utilizing a MATLAB program. Within this MATLAB program, the user can put in specifications for their aerator, lighting, or the heater, and the output of the user interface will let the user know whether the parameters of their system is feasible for a healthy living environment for the plants or the fish.
So in order to collect the data from our physical system, that we built and programmed a temperature controlled relay with Arduino that displays one of 3 warnings based on temperature input. If it's too cold, the heater's on. If it's above the threshold, the heater is off. And if it's within the acceptable range, the temperature is nominal. This info is displayed in the serial monitor as seen in image number 2, where the output of the serial monitor is read by a third program called PuTTY that then converts this information into a text file, which then can be opened in Microsoft Excel to plot the temperature change over time. Now, this is just the digital control of our prototype. Our actual prototype is based on accessible existing materials. We have grow lights for the grow bed, an aerator in the fish tank, heaters in both the sump and fish tank, and pumps in both the sump and fish tank as well.
In our fish tank, we have 2 tilapia that are 1.5 pounds each. Both in our sump tank and our fish tank, we have 2 200-watt heaters that are controlled by the Arduino, as mentioned by Mr. Christopher, and then 2 water pumps in each one, pumping 120 gallons per hour. This may seem high, but this is due to our head height that is needed to push the water up. Just in the fish tank, we have an aerator that gives the fish dissolved oxygen. And then also in the fish tank, we have a float switch that utilizes a 12-volt relay, 3 power outlet, and a float switch. This helps prevent overflow inside the fish tank. And then for the grow bed, we use 2 full spectrum grow lights that give the plants all the colors that are needed. Also inside of this grow bed, we use hydroton, which are fire kilned clay pellets that act as a soil to keep the plants from washing away. This also acts as a pH neutralizer for the water. For the sump tank, we use the sump tank as a 2 fail-safe system in conjunction with our float switch. This allows any water that may overflow to empty out inside of this sump tank, and it also acts as a filter, keeping sedimentation inside of this tank and allows it to settle.
Now, to conclude our work, this novel idea will allow for fresh food production for the astronauts, therefore increasing their quality of life. This system is theoretically feasible as long as the proper equipment will be implemented on Mars. Now, please direct your attention to this video about a quick prototype.
All right, welcome, Team Celine.
Thank you, sir.
Video looks like you had a lot of fun putting your project together.
Oh, yeah.
A
Very
lot of
much so.
fun.
So the audience is already asking questions. Remember, audience, please submit them to slido.com. Use the code TSGC. I'll dig right in here. So how many fish do you expect to be deployed to Mars? I guess based on whatever crew size you were planning on. You can,
So we were expecting to send 168 tilapia at 1 pound each.
so do you send them as full fish or as eggs?
We had the idea of cryogenically freezing the eggs there first so that there would be a low supply of different aspects to actually keep the fish there. So sending them as eggs at first and then having them grow there.
Okay, good. Next question, what is the estimated lifetime of the fish? And what is the plan for turnover without it disrupting the product?
So estimated lifetime of the fish is 9 months. That should cover time from hatching all the way up through breeding in Italy. And then after that, they can be harvested.
That sounds good. Better than the potatoes from The Martian. Okay, then the next question, I guess it relates to the eggs now. So how do the eggs survive the travel to Mars?
They're cryogenically frozen and kept in a capsule, and then when they're brought to the Mars module, they will be lasered at a certain temperature and then thawed.
Okay. Oh, and next question. This is a good one. So with your apparatus there, what will you have to do to adapt to the Mars environment and gravity?
One of the aspects to our prototype that we're adapting as far as the gravity is using those hydroton, the clay pellets. 2 reasons, like Christian was explaining inside of the PowerPoint video, is that so that the soil doesn't actually run off with the water, and also these clay pellets are a lot heavier and stay in place more than the dirt would as far as gravity is concerned, and it keeps the plants in place. Again, as far as gravity is concerned.
Another aspect is the pumps. Since Mars is 1/3 of the gravity of Earth, all we have to do is make the power approximately higher by 3 folds.
Okay, so let me ask, where do you get the hydroton, the pellets?
You can get hydroton from online resources. It's just a fire kilned pellet that is very porous.
So it's already being used now on Earth?
Yes, sir.
Okay. Next question online. Why did you choose tilapia specifically?
So we chose tilapia for their herbivorous diet and their ability to be bred and harvested within the 9-month time span. Looked at trout, bass, even sturgeon, but due to diet and temperature requirements, a lot of other fish were just outcast.
Even crustaceans as well.
And what plants are you growing above them?
You have tomato and basil currently.
Yeah.
Sorry, Christopher.
No, you're good.
And would those be, I assume, transported by seed as well?
Yes, they will be vacuum packed.
Beginning of having the plants initially implemented into the system, it was about maybe a week a week and a half when the tomato plants actually doubled in size.
All right, next question. What was the weight constraint for your design, if there was one? And if so, do you see any areas you could reduce the weight or size?
As far as mass estimate is concerned, we were told that as far as the aquaponics system, implementing it into the initial Mars mission, the weight of this module would be so insignificant compared to all the other elements like the nuclear reactor and then other tools that they needed for the actual mission, since this is just a food production system, that the mass estimate portion of it was not really going to make a huge difference, if that makes sense, for the mission.
Okay, and did you come up with a cost estimate?
For the cost estimate, I believe that we did not entirely have a cost estimate. We have the cost estimate of how much it was for the prototype to make here.
Okay, and last question online, where would the water supply come from?
So initially it would be sent on a rocket in the form of ice to be thawed out later on Mars. The reason why we chose this because it will reduce the fluctuations, during space travel. Once it's actually on Mars, we would need to replenish the water every now and then for evaporative losses. So you would have to find a way to get the water from the environment on Mars. That's something that we considered, but it's outside of the scope of this project. So that is something that I guess NASA would have to find out.
Or we could do as far as continuation for this project.
Very good, very good. All right, so let me ask, what were your biggest challenges this semester?
If I could go first, one of the biggest challenge as far as this semester was actually implementing standards that TSGC, or not TSGC, that NASA has for their design of new products, like the TRL and the DRA-5. And that's one of the reasons why we have a sump and a fish tank, is that we kind of wanted to implement some of the standards that are already currently in use. The sump tank is actually like a two fail-safe system. So if something were to overflow or something were to short out, then we know that the system would not overflow, or water be everywhere, or anything would fail, or it wouldn't continue to cycle.
Okay, great. Thank you very much, Team Selene.
Thank you.
All right, thank you.
Thank you, sir.
Thank you.
Our next team is from Lone Star College Sci-Fair and Team Calypso, working on the NASA Micro-G Next project.
Hello everyone, thank you for joining us today. My name is Alma Gallardo. Team Calypso is excited to present today our project Spacesuit Attachment Quick Release System, a challenge given by Micro-G Next. This semester, Team Calypso continued working hard on revising the selected design from last semester. After receiving feedback from TSGC and considering NASA review, the team assessed and made the necessary modifications to the design to address concerns that arose from our last semester design. We're excited to share with you today the progress and results that we had this semester with our project. Thank you again for attending our presentation.
NASA is planning to return to the moon by 2024 with the Artemis program. On this mission, astronauts will be performing EVAs and they'll be carrying tools on the new XEMU spacesuit. There will be a utility belt attached to the spacesuit, and the belt will hold tools during the EVAs. In order for it to work properly, a quick release system is required to help astronauts work efficiently. NASA currently has a bayonet, probe, and receptacle system, but the system isn't suitable for the environment on the moon. NASA is seeking to update the system that they have, and that's where Micro-G Next comes in. This program gives undergraduate students the opportunity to design and present a solution to real-life aerospace problems. Despite not being selected to continue through the program this semester, the team was willing and excited to continue with the design from iteration to manufacturing. In order to improve NASA's current receptacle system, we needed to identify any problems associated with the lunar surface and any other obstacles. The lunar dust on the moon's surface is very abrasive, magnetic, and adhesive. These properties altogether pose a challenge to the receptacle system's ability to tolerate dust on long mission cycles. In addition, due to the design of the current XEMU, astronauts' mobility and visibility is limited. NASA's current design is not dust tolerant. Dust can quickly fill up and clog the receptacle for the bayonet, thus preventing it from being inserted. Moreover, they have had complaints about the ergonomics for EVA use.
Listed are the design requirements from the Micro-G Next Design Challenge, with requirements 1 and 2 encompassing the most crucial engineering hurdles of the design challenge, 3 through 6 focusing on certain ergonomic features of the design, and 7 through 10 setting design parameters to ensure safety and portability. The ways in which Team Calypso succeeded in meeting and exceeding these requirements will be covered extensively during the testing portion of the presentation. Team Calypso used the requirements set by Micro-G and broke them into these design goals: dust tolerance, tactility, durability, safety, and simplicity. However, these design goals did not supersede the requirements from Micro-G Next. Rather, these summarized ideas help us work through the engineering design process as changes have been implemented from the start to today.
Over the past semester, Team Calypso, in accord with the engineering design process, has created a new version of the aisle design, focusing on addressing concerns and making improvements from the last semester. The new design, while having a redesigned profile, works under the same principles as the previous aisle system, in that the system is composed of an XEMU receptacle and a probe to be attached to an EVA tool. Moreover, the system utilizes the same method of having a ball-nosed spring plunger embedded within the bracket of the receptacle to apply pressure to the surface of the probe when inserted, thus preventing the probe from slipping out without the proper force being applied by the astronaut. The simplicity of this aisle design allows the system to be robust enough to handle the challenging lunar environment and removes unnecessary complexity which would become an added burden to the astronaut. The revised EVA tool probe attachment focuses on reducing unnecessary bulkage and improving the profile of the probe, allowing it to require less precision when entering the receptacle. A 4-leaf clover design was chosen to replace the previous square bracket, reducing the weight while retaining the same level of durability. In addition to this, the size of the probe has been reduced to 1/3 its original size, removing unnecessary weight from the probe while leaving sufficient material on the probe to enable it to hold the required 15-pound tool. Moreover, in response to NASA criticism indicating a potential failure mode, the size of the neck attaching the probe in the bracket has been further increased to prevent shearing from downward forces. Lastly, the profile of the probe has been changed from a U-shape into a V-shape, reducing the friction experienced by the probe when inserted into the receptacle, improving its ergonomics. Like its predecessor, this version of the aisle receptacle supports an open design concept to allow dust from the lunar surface to pass through the system rather than accumulate within it. This is done using slots within the receptacle. The opening of the receptacle and the bracket were angled out to ensure that the opening has the maximum surface area for the probe to encounter for insertion from any direction, thereby improving the ergonomics of the interaction between the astronaut's tool and the receptacle. The modifications done to this aisle system have significantly improved and developed the design from last semester, resulting in a product that better meets all the requirements set by NASA.
For testing of the aisle design, we sought out to manufacture the device using NASA-specified materials. Unfortunately, our selected manufacturer failed to deliver on time for TSGC. Fortunately, the materials are primarily for preventing lunar sample contamination on the moon, and we were able to fully test the device and meet the requirements set by NASA using 3D printing. So, let's go see how the testing went.
Thanks for joining us for our presentation. After carefully taking into consideration the feedback that the team received from both NASA and TSGC, a new version of ISLE was designed, which not only works under the same principles as the original design, but also is more effective. The reiterations make the design less heavy and more durable. Many tests were conducted to ensure it successfully met NASA's requirements. Overall, the team is happy with the results that we had this semester and is excited to have had the opportunity to share it with everyone today.
All right, welcome Lone Star College Sci-Fair. Excellent video. You must have had a lot of fun doing that.
Yeah,
Yes, we did.
did. It's good to be here, Dr. Urban.
So who made the EMU suit?
It was a team effort,
Yeah, it was
primarily
collaborative.
between me and Kyle, but we all kind of contributed to it.
Yep.
Love the cardboard, yeah.
Yeah.
All right, so audience, go ahead and ask questions on slido.com. Use the code TSGC to view and upvote other people's questions. We've already got one here. So first question on your testing, is there any risk of regolith entering the ball spring and preventing it from functioning properly?
Yeah, so the detent pin that we chose, unfortunately, we talked about last semester using the JW Winco spring plungers. Unfortunately, they were out of stock this semester and we were unable to obtain them for our testing. However, something that I did discover is that they use plastic bearings for their dust tolerant seals, and they wouldn't work in a lunar environment anyway because of their temperature resistance not being good enough for the lunar environment. So our intuition is that NASA would manufacture their own spring plungers for an application of this design, and there's nothing we can really do from our standpoint to manufacture anything like that because we're not a machine shop.
Okay, and you mentioned that you couldn't get it machined this semester. So all your testing was done with a 3D printed model, is that correct?
Yes.
And what material was that?
The 3D printers that we used was PLA printers, which is like a plastic type, not as good as ABS, but about the same strength.
Okay, and it still passed all the tests. That's impressive.
Yeah, we were really happy about that.
All right, next question online. Did you give consideration to tool orientation or rotation? And how does this impact your design's ability to engage the locking feature?
John, you want to take that?
Yes, we did give consideration to the tool orientation whenever we were for inserting the device. And the way we designed it was the receptacle does not rotate with any tools. However, the tool can be attached at any degree on the 4x4 bolt bracket. And for insertion, we have a 70-degree area of insertion, so angle of insertion actually, so that the astronaut can insert the tool from any direction, any angle. So
okay, and so that new V design that you showed, that's the 70 degrees?
Yeah.
Yeah, more or less the
Right.
angle of insertion. I have a tool here. The profile of the V allows for angles of insertion from many different directions. Let me get this out of the way. So if you had it coming at a directional angle like this, you'd still be able to slide into place because of the profile. And then, like you said, the bolt hole pattern on the back can be orientated in any direction. And because the locking mechanism is centered on the detent, it can be held in place sideways. Although I don't know why NASA would do it. You could technically do it upside down as well, and it would hold the tool. But yeah, you can do it in any of the 4 orientations for the bolt hole pattern.
Great, great. Next question. Was your sample lunar dust similar to lunar regolith in size, I guess the particle size, and was lunar regolith simulant considered?
Yes, it definitely was. So we use both a flour-based and a baking soda-based. The flour has about a 10 to 41 micron meter size in comparison to the lunar dust with about a 41 to a 300. So the actual size of the flour regolith probably would more accurately represent the lunar dust surface.
Okay, and then on your device, what machining methods did you select for manufacturing of the alloy prototype?
So we are originally intended to manufacture a design with CNC machining, but the machine shop recommended us to go for 3D printed in aluminum instead. So we were planning on doing that 3D printed in aluminum.
Okay, and then if your device came to the market, what would be the cost of it?
We got an estimate of what it will be the price, and the whole assembly is 600, around 600, 300 the probe and 300 the receptacle.
Okay, so
However,
for your
this is-
prototype, that much.
Yeah, but at scale, manufacturing scale, I'm sure that price is significantly reduced. It just happened that machine shop we were working with, working at a single unit scale, is going to have to increase their profit margin because of the nature of our device.
Absolutely, yeah. Prototypes are always more expensive.
Yes.
So what have you learned this semester? What were your challenges and what were your biggest takeaways?
I'll go first, and I'd say my biggest challenge was getting our 3D printers to work consistently. As much as I love 3D printing and the process of it, it was incredibly helpful this semester. We had so many issues with our 3D printers. I was literally working on them week to week to make sure that they were functioning for our device. And ultimately they did work, but certainly it was a learning experience for sure.
Right. And another challenge that we had was the winter storm. I'm pretty sure everybody had some difficulties kind of like accompanied with the winter storm. And for our team, because of the delay that happened, everything that we had planned before from 3D printing to manufacturing got delayed like a week back. So that's and we kind of had to like the emergency meetings in a sense, so to rearrange things to make sure that we meet the deadlines that we had planned and to make sure that we had a solid final design for the showcase.
Yeah, and I'll go next. So we also use different testing simulations. So for AutoCAD, we use that testing software, which that was a learning curve. We haven't, we're still kind of learning through that process of that different software. So that was definitely a challenge using, teaching ourselves that software so we can create an accurate test simulation for that lunar surface.
I'll go next. From a design perspective, one challenge that we really had was the tolerances between the probe and the receptacle, because the detent pin wouldn't engage if it was too loose. But if we had it too close to the tolerance, then it would be too tight for the astronaut to actually be able to remove. And with that, we found that dust didn't want to accumulate in the dimple that we had for the detent pin. So we had to redesign a through hole going through the probe to allow the dust to escape and allow the detent pin to actually engage instead of getting jammed and not engaging at all.
So one of the other challenges that we had was contacting machine shops within the time that we had left, especially with the winter storm that Min just mentioned. We asked those to several machine shops, but they could not work with the time constraint that we had. So manufacturing was a bit of a challenge since we couldn't find a machine shop that could help us on time, and our 3D printers were not collaborating with us either all the time. So at the end, we managed to have a 3D printed prototype of our design that, despite its material, it met all requirements.
Looks like it worked very well. So congratulations. Have you reached out to NASA again with your new updated design?
No.
Yeah.
No, we haven't.
All right. Yeah. For you and for all the MicroGNX teams, I may reach out to our contacts there and just see if they want to take a look at your revisions. I think they're pretty good. So thank you very much, Team Calypso.
Thank you.
Thank you, Dr. Urban.
Thank you, Dr. Urban.
All right. Our next team is from San Jacinto College, and they're the SJC Gators.
Greetings. We are the SJC Gators from San Jacinto College. Our Texas Space Grant Consortium Design Challenge is to create a solar concentrator for extraterrestrial use. The SJC Gators is made up of 3 team members, Daniel Guerra, Ryan Alinger, and myself, Michael Kruger. Our faculty advisor is Dr. Nathaniel Wiggins, and we have two mentors, Mr. Christopher Mendel and Mr. Houston Green. According to the Artemis mission plans, NASA intends to send humans to the moon again by 2024, with special interest in a sustained human presence on the lunar South Pole. There is a need for energy on the moon if people are to stay there, and the sun is a viable source.
Hi, my name is Daniel Guerra, and I'd like to talk about how a solar concentrator could be used on the moon. Well, there are some astounding possible applications. It could be used to supply electricity and lighting for a possible human habitat, or to cultivate plant life on the Artemis base camp. There also exists the possibility of using thermal energy to decompose lunar regoliths producing helium-3 and oxygen. Helium-3 is a light-stable isotope that is currently being developed as fuel to produce energy by nuclear fusion processes. Designing a solar concentrator for applications on the moon comes with its own unique challenges. These challenges include a hostile vacuum environment with extreme temperatures and lunar dust. Lunar dust is composed of very small abrasive particles that float around on the moon's surface, sticking to almost everything. This is problematic for devices with moving parts because once exposed, it will lead to rapid degradation of the device. This means that solar concentrator designs that use mechanical tracking will quickly fail on the moon. A separate issue with lunar dust is that it will also collect on optical surfaces and obstruct light transmission. Now that we have discussed the challenges, let's go over the objectives of our design. Our design abstract requires 30% energy efficiency, and as mentioned previously, the concentrator must not have moving parts and be able to endure extreme temperatures. The optical surfaces must be durable enough to resist scratches and strong enough to endure the stress of a launch. And lastly, the optical surfaces must have minimal lunar dust accretion.
Our design concept incorporates two main components, a cylindrical Fresnel lens and a funnel-shaped receiver lens. The cylindrical Fresnel lens is the means by which this design removes solar tracking. As the sun moves across the sky, this Fresnel lens focuses its rays onto the circular edge of the receiver lens. It is able to collect and focus light from a complete range of angles that span 360 degrees. The design could also be turned on its side as seen in the bottom picture for a possible lunar South Pole application, where the sun rotates horizontally around the horizon. We considered the following measures when we optimized the cylindrical Fresnel lens. The lens needs a small focal length, which reduces the circumference of the cylinder without losing any light. Additionally, the team attempted to maximize the width of the lens to capture more sunlight. The focal spot of the Fresnel lens should be no wider than the edge of the receiving lens to minimize lost light. And we also attempted to maximize the percentage of rays that converge in the focal spot. This included taking measures to minimize aberration, which occurs when rays cross at points other than the focal spot. After testing over 20 different designs, including many with aspherical curvature and designs with grooves facing inward, the team arrived at this design for the Fresnel lens. We ended up with a Fresnel lens that focuses parallel light rays to a focal spot that is 12.5 millimeters wide and concentrates 698% of the original energy density onto the receiver lens. This design is scalable, but this particular model has 844 millimeter diameter and a lens profile width of 253 millimeters with a mass of 7.7 kilograms.
My name is Ryan Ellinger. I would like to present the second lens in our system. We call this the receiver lens. Light enters through the yellow edge shown in the left image. This edge is placed directly at the focal spot of the larger Fresnel lens, and once light enters, total internal reflection redirects the light through the tube into a fiber optic cable. This is a simulation of our Fresnel lens and receiver lens system. Here you can see light rays travel from the Fresnel lens towards the receiver lens and into the funnel. Total internal reflection then occurs as light rays reflect down the tube and out the other end. This Pew analysis chart helped the team determine the best material for our lenses. Each column lists a different material property. The range of values from each column were divided into a 5-point system, where most desirable is 5 points and least is 1 point. The team was excited to discover ALON, or aluminum oxynitride, ranked the highest. It is the hardest material on the list, which will help prevent abrasions and fractures on the lenses. Also, its coefficient of thermal expansion is well beyond withstanding the thermal cycling on the moon. At 2,423 Kelvin, ALON has a very high melting point, which will prove useful under extended periods of exposure to concentrated sunlight. And although ALON has the highest density of all materials in the chart, this is offset by its refractive index. Because ALON has such a high refractive index, the size of the Fresnel lens is greatly reduced, and the receiver lens is able to retain more light, which improves the system efficiency.
The team used Optica EM simulation software to run optical simulations of our design in Wolfram Mathematica. The capabilities of Optica EM software are quite impressive. Here, we were able to input ALON's refractive index data from a technical datasheet into Optica, and then Optica created a function by fitting a curve to that data. This function was then applied to our lenses when we assigned the medium ALON as seen here, allowing for accurate results at any wavelength of light. Speaking of wavelength, the most prominent wavelength of electromagnetic radiation on the moon is 0.475 microns. We ran our simulation with 0.475 micron light rays as seen here. For the shape and pattern of our light rays, we chose a line of parallel rays. The sun rays that hit a given location of the moon are practically parallel, and the line-shaped cross-section of those rays was able to give us the needed information in our simulations. Optica EM also enabled the team to turn on Fresnel reflection equations. These equations are vital to determining accurate and realistic ray intensities as are seen in this intensity plot. The ray colors show the ray intensities from red, most intense, to blue, which is least intense. The team tested over 30 different design options. Optica's STL importability enabled us to test our lenses. We were therefore able to create different variants of our lenses in OnShapeCast software and import them into Optica for testing. Two of the desired Fresnel lens parameters are a short focal length and a focal spot of 6.35 millimeters or less. We were able to use a fine focus function in Optica to evaluate the back focal length and also the focal spot sizes of our Fresnel designs. We created intensity plots and used a find intensity function, which allowed us to evaluate surface intensities, the number of rays meeting a surface, and the transmitted energy through the optical system. This data is crucial in determining the efficiency of the system.
Based on our intensity data from Optica EM, we were able to determine that the Fresnel lens concentrates sunlight at 698%. We were also able to measure that our total system operates at an efficiency of 37%, which exceeds the abstract requirements.
ALON is a very strong material that can handle up to 700 megapascals. This von Mises stress test shows that our Fresnel lens could endure much greater forces than the 9Gs that are typical of a space shuttle launch. While the team is excited about our results so far, more can be done to take this design even farther. Forward work includes further adjustment of the Fresnel lens to improve the focal spot and optimizing the sizes of both the Fresnel and receiver lenses for maximum efficiency. As shown in the picture, it could also prove useful to add mirrors to increase the system's energy output. Lastly, there is still a need to synthesize a method to mitigate lunar dust accretion on optical surfaces.
In conclusion, it has been a fun and interesting journey to work on this design challenge. When we look at all that was accomplished, we are pleased with our results. Our mentor, Mr. Mendel, presented a working prototype of this design concept to the team, and it was satisfying to confirm that this design works using simulation software. The sun offers great potential as a source of energy, and it is our hope that this idea can be used to take mankind even farther, whether here on Earth or on the moon. The SJC Gators would like to offer a sincere thank you to Dr. Nathaniel Wiggins, Mr. Christopher Mendel, Mr. Houston Green, and Dr. Donald Barnhart for their support and guidance. We would also like to thank the Texas Space Grant Consortium and San Jacinto College for giving us this opportunity.
All right, welcome SJC Gators.
Hello.
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 It's like a very good design you came up with there.
Thank you.
So you used a lot of software. You want to talk about the process of learning and using that software briefly?
Yes, that is an interesting topic. We if we're talking about software, we actually started off using the MATLAB software with a completely different simulation. And this was the PhD work of a German student. And we spent the first month trying to understand his work and create a simulation through that software. And after some time, we came upon the Mathematica software with Optica EM simulation capabilities. And this one came with the user guide, which we had to study and learn first before being able to create our own simulations, while the MATLAB software didn't offer much information to begin with. And I would say that all of us as individuals have faced challenges with learning how to use the software. And I would like to allow them to talk on that as well.
Yeah, we spent probably 6 to 7 weeks trying to get the MATLAB simulation to can y'all see me?
Yes.
Okay. All right, because I can't see me, so I was like just making sure. Okay, so we spent about 6-7 weeks getting the MATLAB software to recognize we had to import our CAD models in, or else try to figure out a way to parameterize them. And it was like a slow grind just trying to get basically from scratch a MATLAB simulation. I mean, we had a starting point, but we're making serious modifications. And so, yeah, we finally got, like you said, access to Optica EM. And, it was a lot, while it wasn't, I wouldn't say it was easy to use, because there's so much functionality built into Optica EM. And there were 37 separate documents included in the instruction manual. So you're searching 37 documents to try to figure out how to use it. But once we got access, it was like, boom, it's like, here we go, and we were able to get momentum going and test things out and start to put models in and modify them. And really, we were kind of able to take off from there. And it was just a real exciting time.
I agree.
Yeah, that turnaround was hard for us, but once we got it, that was it.
All right, good. We've got a question online here. So what CAD software did you design your lens in, and what are the advantages of using that?
I'll answer that one. I was our CAD designer for the most part, because I become pretty well versed in Onshape. That's what we use. There's Onshape, which is a free software that it's pretty, really, I think it's gonna probably not be free for too long because it's pretty good. But it's really easy to collaborate. Everybody can see the documents and work on them, and just has a good amount of functionality built into it. And so we used Onshape, and I was able to also, Onshape lets you add features in. So when we started to mess with curvatures of lenses, it was like, well, I want to bind them to different equations. Sometimes for instance, if we're going to use an aspheric curvature, I want to have an equation that's defining my curvature. And we were able to add a feature in for parameterized curves. And so, it really just, that opened the door to all kinds of new possibilities.
Okay, so moving on to the final product now. Were you able to determine an estimate of the amount of power that your lens would output?
Well, so that's kind of I figured we might get that question. And it really depends on how big it is, right? And the intensity of the light rays that are hitting it. So the more surface area you get, I mean, generally on the moon, they estimate it's about 1,370 watts per meter squared is the radiant flux on the moon. And so, if you have a larger surface area accepting a greater amount of light, then you get more power. So I think that's one of the biggest variables. The model is scalable. So, it really kind of depends on how big, that's kind of one of the things, depending on how NASA, if they took it on and they wanted to use it, depending on their purposes, the size would, they would have to just either, you could combine multiple together, multiple Fresnel lens systems together, or you could just, increase the size of one to get the right amount of power. But in terms of exact numbers, I mean, we mostly just, the abstract was asking for an efficiency percentage, and so that's what we went after.
So how did you size your prototype?
Well, I actually started back with, originally, I think I was hoping to get some kind of a prototype, like a physical one. And so I was like, well, if we made it as big, like one in our minds, we were kind of thinking like, it would be really cool if we could generate a lot of power. However, then the size is going to get really big. And so, I ended up, when I was just choosing the dimensions for the prototype, just imagining like, what could I fit in my car, or, kind of a thing, And so I kind of just limited it in that way, to where it wasn't too big, but to where it would be big enough that we could test it out if given that opportunity. However, we don't have our own physical model of what I created, but the simulation software served us well in terms of being able to show that it works.
May I also elaborate on that answer? So I would just like to add that, well, the design is scalable and we took that into consideration. However, we were not given specific payload constraints. So that really wasn't something we took too much attention to, but we did consider the fact that if we wanted to meet those payload constraints, we can make a system of many of these put together to meet those demands.
All right, good. So you have a scalable system that, as you explained, could be used for growing plants, helium-3, heating, what have you. You talked at the end about mirrors. How would you implement mirrors?
So the mirrors could actually be added on the sides around the outer Fresnel lens to reflect light back into the Fresnel lens. All that light that was lost could possibly go back into the lens. Or you could also add the mirrors inside the Fresnel lens itself to adjust the angles as they go into the inner receiver lens. So that would just, any kind of mirrors like that would just increase the efficiency of the whole system.
Yeah, we were able to spend a little bit of time throwing some mirrors into Optica. What we realized real quickly is there's a reason why the popular mirror design is a parabolic mirror that tracks the sun, and is like, well, I could make a mirror when the sun's straight ahead that will focus, all the light, into that receiver lens through the Fresnel lens. However, it would only work for so many hours of that lunar day. So that's a whole nother can of worms. But I think there is a way, to really,
yes,
to really get even more output. But it's kind of I feel like it could almost be its own design challenge, figuring out the mirrors.
We actually spent a significant amount of time exploring that possibility, and we explored features in the Optica EM software, which allowed us to actually experiment with mirrors and create like an adequate system where we can see a confined path of those rays if they were to hit the mirrors and then hit our Fresnel lens and receiver lens. But our mentor recommended that we only proceed with the scope of this design challenge and focus our time on making this design work, and then explore parabolic mirrors as forward work. But it is possible.
Okay, great. Well, thank you very much, SJC Gators. Very good project.
Thank you.
Thank you.
We are going to take a break now, a quick 10-minute break. Session 1 has been concluded. When we come back at 1:35, we will have session 2 with 3 teams, and then session 3 this afternoon at 2:45 with 3 more teams. We'll see you in about 10 minutes. Good afternoon and welcome back to the next session of the TSGC Design Challenge Showcase for Wednesday, April 21st, 2021. We have 3 teams in session 2. First up is going to be Texas A&M Kingsville, and then UT Rio Grande Valley, and then Lamar University. Again, if you have any questions for us, please contact us at the email below, designchallenge@tsgc.utexas.edu. So first up, we will hear from Texas A&M University Kingsville, Timuk Team 6.
Hi everyone, we are Tamuk Team 6 from Texas A&M University Kingsville, and our project is titled Origami Inspired Solar Array for a Large Spacecraft. My name is David Balderas, and presenting with me today is going to be Aaron Rocha, Leslie Carrion, Ricky Cuellar, and Mauricio Fernandez. Starting the presentation is the introduction to the project with some background and the project proposal. Large spacecraft usually require a large solar array due to the large power requirement of the vehicle. The size of these solar arrays can pose a problem fitting inside a launch vehicle, but origami folding methods can be used to help improve the stout packing efficiency of these solar arrays. The video to the right shows a conceptual design created by 2014 BYU PhD student Shannon Zerbel. Our project proposal is to design and prototype an origami-inspired solar array that produces 150 kilowatts of power and fits inside the payload bay of the SpaceX Falcon Heavy rocket. Now to summarize the important objectives and design constraints. The primary objectives of the project include the ability to produce 150 kilowatts of power and to fit inside the payload bay of the SpaceX Falcon Heavy rocket. The primary design constraints include a power to weight ratio greater than 28.7 watts per kilogram, a stowed packing efficiency greater than 26.3 kilowatts per meter cubed, and a total weight less than 63,800 kilograms, which is the low Earth orbit payload capacity of the SpaceX Falcon Heavy. Shown here is an outline of all the work that will be presented today. First, we have the mathematical model increase pattern, followed by the solar array assembly. Then we will talk about the actuation, solar panel assembly, prototype, and then end with the conclusion and future work.
Mathematical model increase pattern, we chose to use a flasher folding pattern because of the volume constraints for the vehicle payload. We did consider an accordion folding pattern that is currently used on the ISS, but due to the flasher's 10-time increase in deployable diameter to folded diameter, we determined it was the optimal solution. We used a Mathematica 12 notebook that sets up the constraints for a general flasher and solves for vertex coordinates for both the crease pattern and the folded form, as you can see on the picture on the top right. On the bottom right picture, you can see that M, highlighted in green, is the number of sides of the central polygon that the pattern will wrap around, so 4 for us. H is the number of axial bands between the bottom and top of the folded cylinder, which is highlighted in purple and yellow, that is 2 for us. And R is the number of rings on the pattern, that was only 1 for us. You can also see in the picture that the mountain folds are indicated with solid red lines, while valley folds are indicated with dashed blue lines.
Now we will discuss the solar array assembly. The CAD model shown to the right is the design created by Tamuk Team 6 in SolidWorks. It showcases the 3 sub-assemblies, which include the kinematic structure, along with the solar panel assembly, and the connecting linkage mechanism, which ties in the solar panel assembly with the kinematic structure.
The first subassembly we will talk about is the kinematic structure. This structure is responsible for supporting the weight of the other subassemblies and deploying the solar array once it's in space. The structure expands to 573 meters squared to allow for the fully deployed solar array and connecting linkage to fit within it. The structure also retracts to 0.35 meters squared to fit inside the payload bay of the Falcon Heavy rocket. The structure will be made out of aluminum 7075-T6, which will give us an estimated 12,500 kilogram weight. Our initial iteration allowed full range of motion, but impacted our ability to retract because of the connectors protruding. An example of a protruding connector is circled in red. This flaw was corrected in our final iteration while still allowing a full range of motion.
Next, we'll talk about the connecting linkage. The connecting linkage is used to connect the solar panel assembly to the kinematic structure by tying each corner of the solar panel assembly to 4 individual connectors on the kinematic structure. The linkage allows for the necessary motion by means of a universal joint between each link and a revolute joint that connects the connecting linkage to the kinematic structure. The detailed design for this mechanism is still being in progress. The solar panel assembly will now be discussed. The image in the top right-hand corner is a layout of our 21 by 21 meter solar panel assembly. The gap size between each panel is a total of 6 times the thickness of the entire solar panel. Theoretically, mountain folds and valley folds are used in origami models with thicknesses, but after iterating our prototype, we discovered that having a gap size of 6 times the thickness allowed for much easier folding, and this is why we decided to go with a gap size of 6 times the thickness. The image in the bottom right-hand corner shows this gap size in the CAD model.
For the actuation, we'll be using an electrical motor that will be expanding and contracting the solar array in 1 degree of freedom. We'll be using 4 rotary actuations that will be attached to the cross-sectional links of the areas that the arrows are pointing to in the figure below. For the table, we have yet to decide the type of actuation we are using, but the 3 we are considering are the Ultra Performance, the Enhanced Type 5, and the High Torque Type 5. We chose these 3 because of the operating temperature, the wide range operating temperature that it has, and the amount of torque it produces.
The solar array will have a total of 21 solar panels and will have a surface area of almost 475 meters squared to produce the desired 150 kilowatts of power. Each panel will have the same 4-layer configuration, which can be observed in the image to the right. The overall thickness of each solar panel will be 0.26 millimeters, which will cause it to weigh 442 kilograms. The flexible membrane, which will hold all of the solar panels together, will be made of a Kevlar cloth and will be sized accordingly to withstand all possible experienced loads. To determine the required Kevlar membrane thickness, many FEA studies were performed on SOLIDWORKS while varying several different parameters. After multiple trials, we obtained the most favorable results when the membrane thickness was 4.5 millimeters with hole diameters of 0.75 meters. As a result, this would make the entire solar array assembly, both solar panels and flexible membrane included, almost 4.8 millimeters thick and weighing about 3,578 kilograms.
For our weight budget, we calculated the weight of all the components in our design by multiplying the material's density with the volume. We got a total weight of 22,134 kilograms, which is way below the constraint of 63,800 kilograms of the Falcon Heavy rocket for low Earth orbit payload.
We created a small prototype of the origami solar array using a 3mm Kapton sheet and various 3D printed components. The components included 1mm thick solar panels, 1/4-inch thick links, and custom connectors for the kinematic structure. The hardware to fix the links and connectors were slotted spring pins of 1/4-inch diameter. The actual assembly of the prototype will be discussed in the next slide. The assembly of the prototype began with the Kapton membrane and 3D printed panels. The membrane and panels were joined together using a thin layer of Gorilla Glue. The panels had a gap of 6 times the thickness between each panel to facilitate folding. Through testing, we discovered that this was a good gap size, and we also implemented the use of stress relief holes based on some advice from Dr. Zerbel. The kinematic structure was put together by hand with the use of pins. We ran into some trouble with the quality of our 3D printed links, but this was quickly resolved by changing to a different spool of PLA material.
In conclusion, the origami solar array assembly designed was able to meet the spatial constraints to fit inside the SpaceX Falcon Heavy payload bay and generate 150 kilowatts of power. Unfortunately, a solar array mechanism of this size did not meet our power to weight ratio and stowed packing efficiency constraints, which are taken from the ISS solar array wings. This is most likely because of our use of only 1 ring for the 4-sided flasher crease pattern. The team switched from 2 rings to 1 ring on the crease pattern to allow for simpler and easier to simulate motion. Reducing to 1 ring caused for a solar array mechanism that was too heavy and had too large of a stowed volume. One of the most important lessons learned is that an origami flasher solar array's performance is greatly reduced when using only one ring of the origami crease pattern.
Some aspects of the project that can be optimized and improved include implementing a different flexible membrane to our design, the addition of a metal frame to the solar array along with an increase of the attachment points on the flexible membrane, providing a more detailed design of the connecting linkage and testing its functionality, improving the rotation ability of the links on the kinematic structure, and reducing the weight of the solar array mechanism overall.
All right, welcome team. So audience, go ahead and submit your questions on slido.com. Please enter the code TSGC and you can view and upvote other people's questions. So this was a very interesting project that you've been working on for 2 semesters now. What would you say are your biggest takeaways from the project?
I would say the biggest takeaway is to find, in order for this design to be practical, the kinematic structure needs to be designed in a way that it can benefit from increasing the ring size of the crease pattern. So in the summary slide, it was the power to weight ratio and stowed packing efficiency of the design was shown, which was a lot lower than the ISS solar array wing power to weight ratios and stowed packing efficiencies. And the main reason for this was because our kinematic structure was designed in a way where it could not benefit from the crease pattern gaining another ring in the crease pattern. So like basically when I say gain another ring, the crease pattern becomes more complicated and it could fold onto itself more. And so when that happens, the height of the stowed solar array decreases significantly by increasing the stowed diameter. But our kinematic structure design was based, or it was not dependent on the height of the stowed solar arrays. So if we could somehow make a kinematic structure that is based on the height of the stowed solar array, then this design would become more practical. So I would say that was the main takeaway.
All right, anybody else have other takeaways from this? So you mentioned the efficiency. What are some typical values for that packing efficiency?
So the packing efficiency, that is going to be the power output over the stowed volume of the structure. So the power is going to be determined by the surface area of the solar array assembly, or the solar panel assembly, and then the stowed volume is just going to be how much space the structure takes up when everything is compact and folded, and that would be the state that it's when it's placed in the payload bay of the rocket or the launch vehicle.
And what was your goal for the packing efficiency?
So we wanted to get a value lower than I'm forgetting the exact value. It was around 28 watts per meter cubed, or I'm sorry, 28 kilowatts per meter cubed, and that was the value that we got from the ISS solar array wing. So we wanted to create a design that we could say was an improvement of that the folding used in the ISS solar array wing. And I think it's important to mention that it was kind of difficult to get an exact value, as the values that we got were obtained from a payload bay report when they were sent into space. So we were never able to confirm whether or not that value was including the mechanism that used to fold and unfold the solar array for the ISS solar array wing. So if that was taken into account, then our values will be much closer to the objectives that we set forth. But it was difficult for us to decide whether or not that those values included the mechanism that deployed and retracted the solar array. So.
Okay, so what other designs has the team looked at for folding?
For the kinematic structure, we looked at maybe a couple of different designs. The main thing that we changed on the kinematic structure was going to be like the connectors that connected the scissor links. So if you saw on the slide, one of the previous iterations that we had kind of had like a hinge for the links that when they folded, they kind of stuck out a little bit. That was something that we looked into, but eventually decided to change because it kind of negatively impacted the size of the kinematic structure when it was fully closed. So that was something we looked into. One of the things that mainly inspired the kinematic structure was the Charles Hoberman ring. It's a ring that was used in a little toy ball that would kind of open and close. That was kind of something that we took mainly inspiration from when creating the kinematic structure. It kind of folds and unfolds the solar array.
Another folding we could have used for the crease pattern, we used a 4-sided, so it looks like a square. For the projects similar to this one, most of the time the 6-sided one was used, and we decided to go with the 4-sided flasher because the panels were squares, and the 6-sided flasher, you see a lot of like really small triangles and kind of like awkward shapes. So we figured it would be easier to and more practical to manufacture if we were to use a 4-sided one with like more rectangular panels.
Okay, related to that, we have a question online. How many prototypes did your team end up having to physically build before settling on the final one?
So for the prototypes, we kind of had our initial. For the prototype, we started with the membrane. So essentially with the panels and then the membrane that the panels sat on. So we had 2 prototypes of that because initially when we made it, we did it with based on the literature, the gap size between the panels would be 2 times the thickness in order to allow it to fold on itself properly. But based off of how we were like when we had it in our hand and tried to fold it with 2 times the thickness, it ended up being too stiff. It was really hard to fold it, as well as the panels would kind of lift up off of the membrane. They would kind of unstick because we used tacky glue adhesive. It's just a crafts adhesive. The panels would kind of lift up. It was really impractical. So we made another membrane with 6 times the thickness, which folded a lot easier. The panels we changed the glue to, instead of tacky glue, to Gorilla Glue, so a super glue, and the panels folded a lot easier. It was a lot better. So that's why we had two prototypes of the membrane, and then eventually we made a kinematic structure prototype. The first one, we kind of had a lot of issues with 3D printing. We had a kind of warping in the links. The holes are kind of a little bit not the perfect size because there was a few imperfections here and there. So we used the first kinematic structure prototype as well as the second membrane to create the prototype you saw in the presentation. And then we were actually in the process of making a second kinematic structure, which kind of opens and closes a lot smoother, but we just didn't have enough time to include it in our presentation because it's still a work in progress right now. So I guess you could say 2 and 2.
Okay, all right, good. And then finally, so we've of course had a lot of challenges this semester with COVID and the winter storm. What were some of your biggest challenges working as a team this semester?
Well, during the winter storm, we kind of weren't able to meet up at that time. So that was kind of a big challenge there. We were some of us, back home, at least for me, we lost power We didn't have power for like a week, so that was kind of an issue there, kind of set us back a little bit. But other than that, we kind of met with each other with face masks and 6 feet apart, of course, following CDC guidelines when we were able to meet. So it impacted us for a little bit, mostly the winter storm, not too much COVID, but we try to follow the rules and stay safe for the most part.
Another challenge I would say that we had was the fact that this project is it's only been done a few times, and so there wasn't a whole lot of literature to base it off of. So a lot of it was just having to, I guess, a lot of the decisions that were made were just based off of our best judgment and our engineering judgment. And we had to kind of work around the fact that there wasn't a lot of work done in this arena. So I would say that that was also another challenge that we had to overcome.
Okay, anybody else? All right, if not, thank you very much, team.
Thank you.
Thank you.
Okay, our next team is going to be from the University of Texas, Rio Grande Valley, and they are Bronkbotics with Machine Learning Human-Computer Interface System, or MHIS.
I am Jesus Guajardo, and we are Bronkbotics. Our project is about developing a machine learning human-computer interface. The main purpose of this semi-autonomous system is to solve the issues caused by communication delays between the Mission Control Center and space vehicles. It takes a relatively short amount of time to exchange information between the spacecraft and the base. It takes approximately 5 to 20 minutes for the Mission Control Center to receive the information. Although that does not seem significant, communication can be further delayed in cases of deep space travel. The longer delays can be detrimental to a space mission and the status and health of the astronauts. The autonomous system is therefore necessary to effectively control the vehicle and maintain efficiency on the spacecraft when the Mission Control Center cannot. Our team's objective is to develop a proof of concept by establishing the requirements that would drive our design towards the goal of creating a reliable system that serves as an onboard semi-autonomous mission control that is capable of handling emergency situations when the user is unable to.
Hello, my name is Aldo Bejarano, and I will be talking about the design challenge of this project. Now, for the design challenge, we would have a semi-autonomous system that would check the habitat in the space vehicles while simultaneously checking the health conditions of the crewmates. The semi-autonomous system would check the sensors located throughout the space vehicle that would monitor things such as temperature, humidity, and pressure. Over time with data, we would be able to detect upcoming emergencies, such as the temperature getting high in one room causing a potential CO2 burst, or the pressure getting high in one room causing a potential blow in the system. And with our sensors, this would over time it would get better with more data we have.
Hello, my name is Gracia Bernal, and I'm going to talk about how we're going to implement machine learning in our project. Our semi-autonomous system will retrieve a personality profile of the crew member operating the system. This profile consists of information such as previous crew usage, including his or her performance. This information will be obtained from the recorded data from the manual input key section. As you can observe in our general design process, the system will monitor the click patterns. It was determined by our client that 2 mistakes will be considered a sub-performance. The semi-autonomous system will analyze the recorded patterns, learn from the obtained inputs, and implement its own decision-making to determine whether or not to take over to correct and decrease human factors that will interfere when handling an emergency situation.
Hello, my name is Bert Bergeni. I'll be going over some proof of concepts, developmental ideas, and general testing of our proof of concept systems. The concept of operations can be summarized as follows. If a critical event is triggered by one of the sensors, the system will expect the crew member to respond in a timely manner. If the response is incorrect for the type of event that's occurred, or there is no response at all, the system will then automatically input the correct responses itself. For example, if a critical event were triggered, and a crew member is unable to get to the input console or is possibly incapacitated, the system will be able to eliminate the problem by itself. The next slide shows design constraints implemented by our mentor. It must be commercially available hardware. This will increase the availability of our system at any given time and also keep the budgets lower than if an engineered on-demand product was designed. The machine learning algorithms also must be commercially available. For our project, we expect to do a majority of the coding ourselves. This is mainly to have a solid understanding of how the system works, or if we ever need to debug any aspects of the components of the system, then we can easily do that and we'll have a better understanding of how it was designed. The next constraint for the system must use space station caution and warning criteria. For this, we've implemented a safety feature which consists of 3 states for any inputs: a ready, arm, and fire. This will allow us to ensure the safety of the crew at all times when dealing with any kind of critical events. Our developmental ideas are as follows. A Raspberry Pi computer will handle all user interface and logic of the system and be made of Python scripting and algorithms, and an Arduino microcontroller will be responsible for relaying the sensor data to the system itself. Now, the Arduino microcontroller is based off of a C++ language, so that's what the coding for that would be consisted of. Doing all of this will allow us to automate many of the features based on the habitat or vehicle parameters that are required to be monitored. In the user interface application, we will also track data such as how many inputs are correct or incorrect to determine if the crew member is mentally able to continue doing the task correctly. We were able to complete general tests for the systems, which include checking if sensors were working as expected, displaying the graphical user interface on the Raspberry Pi unit, and some basic logic commands. For example, if the temperature exceeds a certain range, an LED would turn on.
Hello, my name is Cecil Castillo. When we talk about budget, also part of the hardware. So the proposed hardware for this project includes the following. Arduino microcontroller. The main computer will consist of a Raspberry Pi. We have a series of sensors that relay data to the microcontroller. The camera module possibly will become the facial recognition coding.
Team Rockbotics would like to thank you for the opportunity to present in the showcase. We'd also like to thank our mentor, George Salazar, for helping us along the way, and also
Okay, welcome team.
Hi, how's it going?
Good afternoon.
Good afternoon. So thank you for joining us. Audience, go ahead and ask your questions on slido.com. We're using the code TSGC so you can view and upvote other people's questions about the projects. So this was your first semester, correct?
Yeah.
Yes, that's correct.
So are you continuing next semester?
We are hoping
Yes.
so.
Okay, okay. So so far you were able to get to it was the flame sensor, CO2, and pressure?
Yes, yeah.
Is that correct? Okay. So what kind of testing, have you started testing where you would gather input from some sort of human controller and it would learn from them on those?
We've done a little bit of testing specifically for the flame sensor. So we pretty much would have it would pick up changes in infrared light. So we would kind of put like a candle next to it. And then whenever that happened, an emergency error would sound. And then the user would have to put in the input code that would be correct for that specific situation. And we kind of got that one to work. We weren't able to test the CO2 tester or the pressure tester yet, though.
Okay, and are you learning from just one system or one person, or are you doing multiple people that the system is learning from?
We're doing 3 users is what we set it up for. So we have 3 different users that we're tracking.
Okay. All right. All right. So first question is about future work. So what else would you like to do for this project?
I can answer that. We would like to do different scenarios. Let's say like a scenario where it does like someone can do the correct input, and then second scenario like someone can't answer the correct input, so the machine learning will take over and do the correct input. And then another scenario would be like where the user does an incorrect input, but the machine learning will know, hey, you meant this, and that's something we would like to do later on.
And just in general, just like more testing, because for this challenge, like a lot of data is required in order for the machine to actually take over. And honestly, the data is going to be like the hardest part, just because we want the machine to be accurate and just be as precise as it possibly can be.
Okay.
We will also like to implement facial recognition and also have like 2 different sets of data. One, so the system can learn from it, and the second set of data so we can test it and see how efficient and accurate it is. We're also planning on working on ourselves, like creating our profiles, and that's one way that we can test.
Okay, so you mentioned the hardware you use, that's all commercial off-the-shelf hardware. What is the machine learning software that you're using?
It's mainly we're doing a Python coding ourselves and coming up with some algorithms and stuff just to keep track of everything. And then we're going to use that data to actually compare against.
Okay, great. So this has been a challenging semester, especially for a first semester team. What were some of your biggest challenges and takeaways as you were working on this project this semester?
Honestly, for me personally, I think it'd be like getting everyone together to like work on it, because like, you know, we're at home. It's like we obviously like it's just a lot harder to like, okay, when are you guys available? And like instead of like just everyone going to one place and then having to work on it, like we're at the comfort of our own home. So definitely working together has been harder. It was hard in the beginning, but we got used to it as time went on. So yeah, that was the most challenging part for me, at least personally.
Yeah, another one of the big one is most of us are all electrical engineer majors, and we haven't really taken that many computer science classes yet. And, you know, the project is almost, 90% all coding and computer science. So that was one of the biggest, setbacks for us.
Another, apart from like the winter COVID, we also have faced the winter storm over here in I guess you could say the valley. It was not just 1 week, it was like almost 3 weeks where we couldn't have much power or much of anything, or even water. So it was hard to try to work on something when we were facing other problems.
All right, I don't see any more questions from the audience. Do you have any parting words you want to say about what you're going to do next semester?
Yeah, definitely we're going to have the working model ready. We want to be able to demo it, and we also want to be able to, if we do the in-person presentation, we want to be able to, on the actually at the event, be able to create a new user profile. That way we can kind of simulate the different tests that would be happening.
That sounds great. I'm looking forward to doing this in person next time. Let's hope we can do it. All right. Thank you very much, Bronkbotics.
Thank you for your time.
Thank you, sir.
Yeah, thank you. Have a good one.
Thank you. All right. I am told that all of our Cardinal castaways are ready. So we'll start their presentation a little bit early. So next up, Lamar University Cardinal castaways. And they are looking at an alternate treadmill for exploration missions.
Hello everyone, we are the Cardinal Castaways. We are representing Lamar University for the Alternate Treadmill for Explorations Missions THGC Design Challenge. Our outline for today's presentation consists of THGC design specifications, our design concept with our calculations and platform diagrams, also our element analysis and different types of exercises we accomplish with our design. This is our team members from left to right. We have Rich Healy, Dushara Sahan, Christian Chavez, Isaac Santillan, Edgardo Ramirez, and our team leader, James Furby.
Now for our design challenge and project background. The main focus of our project was to come up with an idea to mitigate the physiological effects that crew members in space experience during their exploration missions. So basically what we had to do was we had to come up with an alternate exercise equipment similar to the treadmill. The reasoning behind that was that the original treadmill is too heavy and too big. So we had to design something similar that had the same benefits as a treadmill. Now for the TSGC Design Challenge specifications. We had to make sure that the crew members were getting the appropriate impact and functionality of the exercise as well. Some of these things are the impact of the foot, just like whenever you're running or jumping, that vibration sensation that goes through your spinal cord and so forth. So we needed to basically simulate gravity in space, although we did have some constraints and factors to consider. Some of these constraints and factors were basically it can't be too big, you got to keep the mass under 100 pounds, making sure the volume of the equipment wasn't too big, and also being aware of the physical benefits of the treadmill and how it was going to be applied onto our new concept. For the areas of concern to take note of was making sure that the astronauts were getting the necessary exercise. This was very important because one has to consider an environment in microgravity. When the human body is out in microgravity, it tends to lose bone and muscle mass. That's because of the change of cardiac performance, which are some of the more detrimental effects of being out in space. As you can see from these charts, the aerial bone mass density percentage changes while in space.
In our initial concept for the exercise platform, we envisioned the user would move left to right over approximately 3 feet to allow some movement and associated required impact during exercise. Pulleys were to be fixed on the ends of the equipment. The platform is continuous, as will be seen in the mock-up photos later. The 3 blue lines are just 1 foot superimposed segments. In the center position, the lateral forces of the elastic are balanced. When the user is in the extreme left position, our calculations showed that lateral forces would be excessive due to the extreme angle of the more distant pulley. In a later iteration of the concept, shown at the bottom, the team decided to use moving pulleys that would move with the user. This, plus putting the track on an angle, served to reduce the severity of the angle, thereby reducing the calculated side load of the user to an acceptable level. Here we see the internal movement of the proposed movement system. Note that with the operator in an extreme left or right position, the opposite pulley is closer to the user and in a lower position, which reduces the angle of the elastic to the operator. This movement mitigates the lateral side pull experienced by the user. The frame for the platform is proposed to be built from titanium. Titanium was chosen for its desirable weight and strength properties. The model calculated weight is 66 pounds and appears to perform well in the FEA for the frame. This weight easily falls within the design requirements. The frame skeleton was modeled as 1-inch square tubing with 0.15-inch thick side panels and 0.2-inch thick top panels.
For the finite element analysis, we chose to do a 400-pound impact on a location that we perceive to be one of the weakest on the platform. The structure, being of skeletal tubing, has several overhanging locations. These locations are the weak points of the surface. The surface is made up of 8 equal squares with overhangs in the center of each. We chose to use a single square to impact with the entire force, representing a bad case scenario for the structure. The location chosen is denoted by the red circle in the displacement analysis. During the impact, the surface of the platform only experienced a 0.04 millimeter of displacement, proving that the design is incredibly sturdy and capable of supporting intensive exercising.
For the construction of our prototype,
We were able to imitate our design using lumber rather than the preferred materials such as aluminum or titanium. As you can see from the pictures, the model came out to look pleasant and properly functioning.
The three photos shown represent the three extreme positions a user can take on the platform: the center, the left, and the right. While in the center, the user would experience the desired force of gravity and no lateral forces. This is because of the angles of the cables canceling each other out, as shown. But as you can see, due to the changing angles as the user moves to the far left or to the far right of the platform, they will experience some lateral forces, though these forces have been decreased significantly due to the pulley system. The renderings below show the position of the pulleys themselves as the user takes the various positions. Here we explain the difference in lateral and vertical forces between our pulley system and one that would have the pulley locked onto the sides of the platform. As you can see, both systems would experience relatively the same vertical force regardless of the user's position on the platform. The main issue comes with the lateral forces. While both systems would experience no lateral forces in the center, as the user moves to the edge of the platform, both systems would significantly increase. But by having the pulleys move with the user and decreasing the overall angle between the user and the platform, we've managed to significantly reduce the rise in lateral forces on both far ends of the platform from 66 pounds down to 26. This makes the platform much more stable and usable for safe exercise. Here we show the calculations for the simple example of the user on our platform moving from the center position to the far left position. Position 1 starts with the user having a 200-pound y-axis force, representing gravity, and a 0-pound x-axis force. As the user moves to position 2, the y-axis force will increase to 223 pounds, which is still very usable. The x-axis force, however, will increase to 26 pounds. And while this is a significant reduction from 66 pounds, 26 pounds is still a lot to have on the side while exercising. But modifications to the waist width and the angle difference can reduce that 26 pounds significantly.
Here are a few exercises that can be done in a 2x3 foot space using the lateral movement platform. You can do jumping jacks, squat jumps, side to side jumps, even mimic jump roping. And with a platform that has multiple activity gains, you can do yoga, boxing in place, and even do Dance Dance Revolution. Upon the completion of the prototype, the team was finally able to transform their design concept from a visualization into reality. After a few test runs, numerous benefits were concluded in which will apply to not only the user, but NASA as well. As seen from the prototype construction, a main benefit is the simplicity of this design. This will lead to easy maintenance as the number of tools used will be kept at a minimum. Furthermore, considerable benefits are having the ability to retain spare weight for strength reinforcement, having the option to store items due to the platform being hollow, and maintaining the usage of power at an absolute zero. In conclusion, the team was capable of designing and constructing a prototype for the duration of the fall and spring semesters to which checked off each specification initially given by TSGC. The Cardinal Castaways would like to greatly thank Lamar University professors, Dr. Zhao and the late Dr. Ong, for providing assistance to our team when needed. We are also thankful for our mentor, Philip Callan and his associates in regards to steering our design onto the right direction. Most importantly, we are grateful to be given such an opportunity to develop and present an idea with the potential of it being used on future space explorations. To TSGC, the Design Challenge teams, and the viewers on YouTube, thank you all.
All right, thank you, Lamar Cardinal Castaways. How's everybody doing?
Pretty good. Thank you.
All right, audience, as a reminder, you can log on to slido.com to ask your questions. Enter the code TSGC, and then you can view and upvote other people's questions online. So while we wait for the audience, let me just ask you, you got to finally build a prototype out of wood. Did you all get to test it?
Yes, sir. Yeah, I personally got to test it, and everything seems, it's very solid. I wish we were able to actually use steel or aluminum just to kind of see how that would work, other than the lumber. But all in all, it was pretty cool, for sure.
Excellent, excellent. And so I guess you met the mass and the volume constraints, as far as you know, and the power constraints?
Take that one.
Take that.
Actually, we come in at 66 pounds for the frame, with the power being 0 because it's purely mechanical system. The volume, we calculated it for a 6-foot individual, which came out to about 36 cubic feet when he's standing on the platform. But when jumping, we gave it at least 2-foot clearance for jumping, which comes in right at 48 cubic feet, which is under the 50. So we hit the mark on just about everything by a good margin.
Okay, and it's 2 feet by 3 feet. How thick is it?
1 foot.
1 foot? Is that a necessary clearance for something, or could you make that shorter?
That's one of the future considerations we had, was the ability to actually shorten the platform itself. Currently, it does allow for enough clearance for the rail system, but it's also not necessary for it to be that thick. We can probably easily trim at least 3 to 5 inches off of it.
Okay. All right, we've got a couple questions here online. So compared to running, I guess, is there a concern that the product does not address the same benefits as running, although it is able to do other exercises?
When we talked to our advisor, one of the main concerns that they were showing, there are 3 major concerns. One is the bone mass density, the cardiovascular fitness, and the sensory motor fitness as well. The bone mass being one of the greatest considerations, because whenever you're running, you require an impact of 2 to 3 times the force of your body weight on your foot to actually send a shock up your skeletal system to give your bones that little bit of damage so they can grow back. And that was the main thing we wanted to focus on, with the ability to jump and just to kind of run in place, that someone would be able to experience on the platform. Now, it wouldn't be the exact same benefits as a treadmill, but given the massive weight and size constraints, we were trying to get as close as we possibly could.
Right, and of course, 0 power, which is a definite bonus.
Yes, sir.
Next question. So what are the next steps for this project? Are you taking it anywhere beyond this?
Not to my knowledge. I mean, this is our last semester for all of us. We're going to be graduating in less than a few weeks now. It would be very nice if NASA were to ever consider the project. And I mean, but besides that, we don't really have a personal place for it to go.
Okay. And you were all mechanical engineers. What were the most, out of the mechanical engineering area, things that you had to do for this project?
So I'll take it, but obviously the FEA was important. Also, we kind of went back into our physics training to do some of the early calculations when we realized that with 60, 70 pounds pulling on somebody's hip to the side, that was going to be both hazardous as well as just a uncomfortable motion to learn. So we kind of were able to seize on that. And then obviously the construction phase was pretty useful, just getting our hands on something. Probably in a perfect world, we would have envisioned getting into a shop, maybe doing some welding, but it was a concession just with the lack of access to the lab.
What were your cables made out of, and was it the material you envisioned?
The cables that we used were just some simple rope. the main platform itself it wasn't the full functioning platform that we envisioned as our design. It's more of a mechanical demonstration model, just showing the movements of the pulleys. The actual one we wanted to eventually use was the same cable material that they use on the treadmill, which is actually a modified surgical tubing. And they chose that because of its ease of use for maintenance and replacement if necessary, like if it snaps or anything.
Okay, and if it does snap, is there any safety hazard associated with that?
I mean, besides the actual tubing itself hurting someone, or someone flying off the platform whenever it actually does snap because they're held down and they're exerting force below them, I can't really foresee anything major. I mean, at the end of the day, it would be some sort of surgical tubing, which doesn't really have that much of a cutting capability or anything.
Okay, we have a couple more questions online here. Oh, is there a concern with the astronauts exerting forces on the station itself as they exercise?
There actually is, and that's something that the current treadmill that they use on the International Space Station has, what we were told by its designer, actually a near 1,200-pound stabilization system that keeps it from exerting any sort of noticeable force on the space station because they were concerned with vibrations. But the actual attaching anything for our system was outside of the scope of the design. So we thought that we just kind of leave that how it is. And if necessary, you could design or modify the same treadmill system to apply to that as well.
Okay, and next question. This might be beyond the scope of your project, but did you test how much atrophy was reduced by using your product as opposed to what astronauts use currently?
No, sir, we didn't do anything like that at all. That's far beyond the scope of our project.
No sweat test of using your product versus running?
No, nothing like that.
Okay. All right. I guess, do you have any final takeaways you want to give the audience before we break here?
Yes, for sure. I'd like to mention our professor and advisor. He was the internal dean for the engineering department at Lamar. He actually passed away in January due to COVID. And that was definitely, this being our last semester, coming into the semester and hearing that devastating news, it was pretty sad. It was very upsetting. He was a great teacher, great professor, great advisor, and it was way too soon for him to, pass away, I have to say.
Thank you. Yes, all our condolences. He was a great friend to TSGC for many years. He will be missed. All right. Well, great work. Thank you, Cardinal Castaways.
Of course. Thank you.
Thank you.
All right. That concludes session 2. We'll take a break until 2:45. So we have an extra couple minutes there. When we come back, we'll start session 3 with our final 3 teams of the showcase this semester. Welcome back, everyone, to our final session on day 2 of our Design Challenge Showcase. We have 3 teams coming up this afternoon: UT Tyler, UT Austin, and Texas A&M University. If you have any questions, please email designchallenge@tsgc.utexas.edu. First up this session is the University of Texas at Tyler, Team Vanguard, and they are working on the MicroG Next project.
Our objective is to design 2 interlocking components with a quick release for a spacesuit utility belt. This will develop a quick, reliable process for astronauts to engage and disengage their tools to increase the efficiency of a spacewalk. The quick mechanism will operate manually in microgravity, function in extremely cold weather, and covered in moon dust. The male end will interlock with the female end, and a safety latch has been added for no accidental discharge. Here is a picture of the old method of how astronauts would disengage and engage their tools. NASA has implemented the Artemis program in 3 stages. They return astronauts back to the moon in October 2024. The first female astronaut and next man will be landing on the South Pole region of the moon, where they will be mining for ice. Moon dust is highly problematic for astronauts' equipment. Moon dust has angular geometries and sharp edges due to the moon being in a vacuum. Moon dust has a collection of positive charges due to the photo emissions, and a collection of negative charges because the transmission of electrons goes to a lower energy stage. Lunar dust also becomes ferromagnetic because of the significant presence of iron, which can be problematic to the astronauts' equipment if giving off a magnetic field. The team set off with 3 initial materials: aluminum 6061 for its excellent machinability and formability, good resistance to weathering, reasonable strength, and low weight; stainless steel for its high ductility, high strength, and good resistance to extreme temperatures; and Teflon for its neutrally charged surface, low friction, and low weight.
I want to take a moment to talk about our specifications. When we came into this challenge, we were given 14 requirements that had to be met. We broke those into 16 specifications in quantitative, qualitative, and for safety. Mike already hit on the materials on the quantitative section, but I want to hit on 3 more points: the assembly volume, the assembly weight, and the load capacity. These are all crucial for any NASA mission because, you know, the saying goes, to send 1 pound into space costs $10,000. So we wanted to make our project as small as possible, but as efficient as possible. Let's take a look at the qualitative section. The qualitative section is a little bit more intangible. We want to work on making our device as user-friendly as possible. So if the device is on your hip, you can look any way you want to and use the tool, but also only use it with 1 hand, leaving 1 hand free to do whatever you need to do. Now let's take a look at the most crucial section, safety. We were told to minimize risk as much as possible. Our team took that a step further and we eliminated any risk possible. We have no sharp edges on our projects, no pinch points on our project, and we tried with so many different gloves to get our fingers stuck in our device, and it never happened, making our device one of the safest ones out there. Now let's take a look at what this device looks like in the final prototype, cycling on the screen. Now this is the assembly and disassembly of the device. It breaks down into 3 major parts: our female end, which goes to on your hip, the male end, which attaches to any tool out there, and then the roller catch and safety lock, which joins the 2 together. That roller catch holds the piece in place no matter what the astronaut is doing. Are they jumping around? Have they fallen down? Has lunar dust got into it? It doesn't matter. The safety latch and the roller catch will keep it together.
For the manufacturing process, our team initially started off by printing the design with a 3D printer. Our team performed a total of 5 prints of the entire assembly, and design improvements were added after each print. We wanted to see how we can improve on the existing design and also confirm functionality of the system. As well, we wanted to ensure proper fitting of moving elements. If there was ever any weakness with our design, we went back and redesigned those parts. Here you can see the picture of our final PLA prototype. We have the male end, female housing, and the entire assembly. After ensuring the 3D printing version of the design was good and everything worked properly, we went to a machine shop, and with the help of the staff there, we were able to manufacture our final prototype. Our final prototype was manufactured in Abel's Machining Services located in Stafford, Texas. Our team was very much involved with every step of the manufacturing process. The female housing is CNC machined and is made out of aluminum 6061. The male end is also made out of aluminum 6061. The security lock and the roller catch bottom plate were made out of Teflon. Here you can see the picture of all the components of our design.
So as Monica mentioned earlier, we had 14 requirements we had to meet, and two of the easiest requirements to test for were the weight and dimensions of the prototype. After construction of the prototype, we weighed it and found it to be about 0.56 pounds, which is far under the 2-pound requirement. Also, the device fit within the 4-inch by 4-inch by 3-inch volume. A large part of what we were testing for was the manual operation of our device. About 5 of the requirements rolled into one, those being you need to be able to use it with a thick glove, such as a ski glove or a lineman glove. You had to be able to use it with one hand, out of line of sight, and it had to be easy to operate. On the screen, you can see us doing our moonwalk test with a 15-pound kettlebell attached to our quick release system. There was no deformation, no damaging of the system in any way, and it was able to hold the 15-pound weight with ease. One of the most important tests we performed was the lunar dust simulant test. We wanted to make sure our device was operational in a multitude of grain sizes. You can see the 4 grain sizes we chose from 4070 mesh down to 2500 mesh, which is a very fine clay-like powder. We submerged the device in each of these and cycled it 10 times without any difficulty. And then we mixed them all into a slurry and tried to combine them all into a more realistic composition of grains, and found the device operated nominally. After meeting our 14 requirements, we wanted to go a step further and make the improvements we thought would help our final mechanism. On the screen, you can see on the left the double roller catch, and on the right the male end rod and plate. These are the pieces that are going to be under the most stress and strain, so we wanted them to be easily replaceable. The roller catch comes straight out of the female end, and the rod unscrews from the plate so that you don't have to replace the entire thing in the event of damage. For our future work and improvements on our project, one of the first steps we'd like to do is anodize the aluminum in our school colors. Go Patriots. Another future work step would be to add a spring washer to the male end rod. What this would do is keep the tension between the male end rod and the male end plate, making it less likely for them to actually separate. Another improvement would be to create a tap hole through the female end all the way. We realized that it might potentially trap gases where the screws go in the cover plate. So one of the fixes would be to drill a hole all the way through so no gases are captured.
One of the other elements to our project is the need to quantify the total cost of the prototype and production. And so early on in the semester, we recognized that we could implement a variety of techniques, from 3D printing in alloy to classical machining and CNC machining techniques. We went ahead and selected CNC machining because of its affordability and overall turnaround time. The team had budgeted roughly $1,000 for the prototype. That includes the overall cost of materials as well as labor hours. As is pretty evident, with COVID-19, it was very difficult to access machining facilities and equipment, and so a portion of this project had to be outsourced to a local machining shop out of Stafford, Texas. Though the team was fully involved and immersed during the whole manufacturing process. The end cost of the prototype came out to be $875. That cost is inclusive of both materials and labor hours. And in typical engineering projects, it is not out of the world, right, to see a labor hour charge of roughly $80 per hour. And so this is what we had to absorb in order to deliver on the project expectations. I'd like to take a moment to also acknowledge all of the support that we had throughout the course of the last 2 semesters. First, our professor, Al-Sal Shalash, who is our advisor, and then some of the staff from University of Texas at Tyler, including Dr. Bearcat, the department chair for mechanical engineering, and Dr. Andres Garcia, who is the director of the Houston Engineering Center. Without their support, all of the hard work that the team was able to showcase could have not been possible. Thank you, and we'll open the presentation for questions.
All right, excellent. Thank you, Team Vanguard. Welcome.
Thank you for having us, Tim.
Absolutely. So audience, a reminder, go ahead and ask your questions on slido.com. Use the code TSGC. You can view and upvote other people's questions. There was one question here that they withdrew it because they saw your test. Was there any time that any material got stuck during your tests?
Sure, yes. Zachary, would you like to take that question?
Yes, there were times that it got stiff and kind of stuck a little bit. There was no time that you could never actually disengage it. You just had to apply a little bit more force than normal. It's usually with the larger grain sizes that became a problem. It kind of acted like a wedge in that channel sometimes. But on our main test, the slurry test, it never got caught once.
Yeah, I think I'll add on to that. So during the lunar dust simulant testing, we looked at a variety of mesh sizes, including 4070 mesh, 100 mesh, 200 mesh, and 2500 mesh. And the total range in micron sizes that spans is as high as 400 and as low as 5 microns. So with respect to testing, you know, we put the prototype, both the PLA prototype from the prior semester and the revisions that came afterwards, but also the final prototype in alloy, aluminum 6061, through those paces. And like Zach mentioned, in none of those cases did it really fail. I saw the question from earlier on the if it ever got stuck. You know, in the design there is a hole at the very bottom of the female housing that is put there on purpose, right? It's put there to drain any sand which may accumulate, or any lunar dust which may accumulate on the interior. And so we thought about that as well during the design phase to make sure that there was no accumulation on the interior part of that mechanism.
Okay, and I had not thought about this till now, but did they discuss any sort of larger pebble size, or would that affect your mechanism?
Unless the pebble's large enough to not fall through the hole at the bottom, which is about a 1/2 inch by 0.38 inches, then it obviously it would just block the entire mechanism, but anything else should be able to fall right through.
Okay, great, great. And I saw you tested it in a variety of different ways, did your moonwalk. That was great.
That was fun.
Yeah. So how many different prototypes did you have before you came up with this final design?
Yeah, so for that one, I mean, it was a team effort, right? I think originally we started with roughly 5 or 6 different concepts, refined that down to a leading 3, and then refined that down to a leading 1, which changed about, oh, I don't know, guys, you think it's about 10 times or so, you know, as we tried to improve the roller catch mechanism that was going to hold the male end onto the female end, changing the geometry of the channels, right, for drainage. And then we incorporated into the tool itself, or excuse me, the device itself, you know, a safety feature, right, to keep it locked to avoid any inadvertent disengagement of the tool. And we found that, you know, we wanted to have something that was with the astronaut in mind, right? We wanted to make sure that if they wanted to customize it to whatever felt more comfortable for them, that we took that into consideration. And so that's why we made the safety latch that you can install on either the left or right side of the mechanism to affect the locking feature. as a matter of personal preference, I'm a right-handed person, but there are left-handed people out there, and typically you would want to configure a device or want a device that has that in mind, right, to make it comfortable and easy to use.
All right, perfect. And so we've had a lot of challenges this semester with COVID and ice storm and just trying to meet. So what were some of your biggest challenges and your best takeaways from the end of the semester?
Monica, would you like to take that one?
Of course. For us, our main challenge started in between our fall semester and this one, and that was with the COVID restrictions and everyone respecting guidelines as much as possible, was finding a workshop that could build our device and let us be involved with the process. Just that search alone, I think, took over a month, and that was in constant communication with different shops, making sure they had the resource and the time available to us. We landed with Abel's Machine Shop, and it was a perfect fit.
Anyone else have some thoughts on that? What you
I
personally?
can add on to that one as well. Yeah, so I would say due to the restrictions for COVID, we were not able to meet as many times as we wanted to. That kind of, if we could meet more, that would have been great. And we met a couple of times, and those times were very helpful to progress the project.
Monica hit the nail really well on the head, though. We really wanted to avoid just sending it off and have someone machine it with us having no idea how it was done. So having a local machine shop with Mr. Abel Perez was really helpful to be able to get there and talk to him and see the methods that he would construct it, and it was really helpful.
Yeah, and if I may add to it as well, one of the key things that we spent quite a bit of time on was really diving deep into the various manufacturing techniques that are out there. With respect to 3D printing, maybe metal sintering, right? We really considered that as an option because at the time we were under the impression that because of the geometries of the female housing, that it was too complex a design, right, to manufacture via typical techniques. And so this is where, reaching out to people that have been in industry machining for such a long time, becomes advantageous. And so that's what we found with Mr. Abel Perez, right? His shop. He was willing to spend, between 3 hours minimum. I think we'd at least spend about 6 hours with him just talking about, his experience and what we could adapt, right, on our device to make it more simple to machine. And so, we smoothed out certain features on the interior and, changed some of the other geometries there. But I have to say that was one of the challenges, was really locating a place that could do or help us with the machining within a turnaround time. And at the time we were targeting, no more than 7 to 14 days. And so we were really happy to find somebody that was able to achieve that and help us deliver on the project at the end. So
that is a great outcome that you were able to find someone to help you and support the teams. That is wonderful. All right. I guess last question. So have you had any other contact with NASA Micro-G Next with your new design?
No, since the news came out in December that none of the TSGC teams advanced to the Micro-G, at least for our challenge, right? We haven't really been in contact, though. We've been observing the overall progress of the competition, which I think is kicking into the testing phase here in June. So if there's any way for us to get in contact with them, we'd be very much appreciated.
Yeah, as I told the last Micro-G team, I'm going to send at least your videos to the coordinator and just say, hey, our teams continue to work on them. They've improved their designs. They're excellent. I think they would compete along with any of the others at the highest level. So congratulations and great work. Thank you, team.
Thank you very much.
Thank you, sir. Appreciate it.
Thank you.
Okay, our next team comes from UT Austin, and they are the NASA camera team.
Hey everyone, we are Team NASA Camera. My name is Andrea.
My name is Shelby.
My name is Christian.
I'm Pearl.
And we're going to talk about our project today. Our faculty advisor is Dr. Maruthi Akella from the Aerospace Engineering Department at UT Austin. And we have our sponsor, NASA. Chatwin Lansdowne is our NASA and TSGC mentor who's helped us through this project. So we're going to go through our project's background, our objective, our requirements and constraints we ran through, some of the prior art research we've done, our design solutions and evaluations of those solutions, our engineering analysis, and lastly, our conclusions.
So I'm going to start out talking about our project background. And so the context of the problem that we're examining today is that NASA has an obligation due to its mission of education and advancing knowledge to capture video of astronauts working on the moon. But this video is extremely difficult to capture as astronauts have so many tasks to complete in such a short amount of time that taking up a whole astronaut to just video record and take pictures is a potential waste of time for where they could be working on other tasks. And the lunar environment is very relevant because NASA, through the Artemis program, is hoping to land the first woman and next man on the moon by 2024. So our project is to explore the feasibility of using a camera drone in this lunar environment. And if it's proven feasible, or we can come up with different ways to make it feasible in the future, a lunar drone would allow astronauts to focus on these other important tasks while still capturing video and photo evidence. And so just some background on camera drones in general. So they've been used both on Earth and in space. And on Earth, I think most people are familiar that they use 4 fans to propel and maneuver. And the main constraint to flight time is battery capacity. In space, there have been multiple successful drones that have been used both inside and outside of the space station. Most are propelled by nitrogen gas canisters, and the main constraint is the amount of propellant that was brought up. And then in the lunar environment, it's a completely unproven concept where we've determined the main constraint is going to be the weight of the drone and propellant.
Problem statement. So this is our problem objective. We are aiming to complete a feasibility analysis prototyping of a camera drone platform that can follow astronauts on the moon. And at the end, we are going to be describing the technology and the materials that is required to make this product. And we also researching other patents that may be creating similar lunar technology. Our main focus has been utilizing lunar regolith as a propellant of the drone. The key to the feasibility of this concept is how quickly and efficiently you can accelerate lunar regoliths.
Requirements and constraints. So the only quantifiable design requirements that we have for the function of our drone is that it needs to be able to fly and record for at least 20 minutes, and it needs to be capable of carrying at least 100-gram payload, which for our case would be a camera. Other than that, we seek to minimize the size, weight, and power requirements of the drone so that NASA can cheaply manufacture them and bring them to the moon. And it needs to be capable of operating in a lunar environment. So that would include withstanding intense radiative heat and being able to survive in the lack of atmosphere. Now our spec sheet. Most of the variables couldn't be determined since they're all so intrinsically linked together. For example, the weight, power, and thrust are all very, very closely tied together. If you can make the weight lower, you can have less thrust and therefore require less power. So really it all depends on the type of materials that we use and how low we can get the main weight to reduce the cost of transporting and building the drone.
Prior art. So the table on the left side are the possible propellant, propulsion, and power methods that we have been referring to as we develop a project. For propellant, we filed 2 patents. For propulsion, we filed a patent that describe a design of an electrostatic ion thruster that can work in outer space. And for power, we have 3 other options, as you can see in the table. On the right side, we also study the previous applications of drones used in outer space. These drones have not been functional or used in lunar environment yet, but we did study the previous design of a specific example, a Sprint camera platform. This device released nitrogen gas from a pressurized canisters to keep the drone aloft. This influenced us to study the use of pressurized gas in conjunction with lunar regolith.
Next, I'm going to talk about our design solutions and evaluations. Our decision-making process began with background research and structured brainstorming for what solutions we could think of. Then we considered some further research on the feasibility of each of those solutions and calculations, which then fed into our Pew chart, which is a way for us to have a comparison of design options with the values that we were coming up with from our calculations. And the results of this Pew chart gave us the potential solutions for feasibility. So this is an example of one of the Pew charts we made. We were comparing 3 different power sources, which are nuclear, lithium ion, and a solar cell system. And then we also had a Pew chart for propellant, which those options were lithium hydride, nitrogen gas, and accelerating lunar regolith or lunar dust. So what we found after considering all of the power criteria and propellant criteria, which mainly was size, weight, safety, and more, we came up with the final results that we should continue looking into lithium ion as the power source and lunar regolith as our propellant method.
For our engineering analysis, we decided to take a deep dive into the feasibility of the lunar regolith concept. So since our design will need to carry its own propellant, the drone will be governed by the rocket equations. So using the ideal rocket equation on the bottom right there, combined with a known thrust value that we know we'll have to achieve, we were able to find preliminary values for our lunar regolith mass and exhaust velocity requirements. These are those results. One thing to keep in mind is that these results are for an empty weight of 2 kilograms. So this assumes that the platform of the rocket and the payload of the rocket are included in that 2 kilograms. Other than that, we have the properties of the lunar regolith and some geometrical constraints on our rocket and nozzle. You see that we will require a propellant velocity of 295 meters per second to maintain flight for 20 minutes with a propellant mass of 13 kilograms. I would like to add that that's quite heavy and quite fast. So maybe already this is looking not to be feasible. Next, we created a simulation. We were able to track the loss of propellant mass over flight by adjusting the exhaust velocity continuously based on remaining propellant. Basically, what that means is as the mass of the propellant was lowered over the course of the flight, we adjusted the exhaust velocity to slow down to compensate for that, so that a hover state is maintained on the moon. And here are the results of that simulation. As you can see, in this example, we started with 10 kilograms of propellant, and it seems to last us about 9 minutes, which already I think 10 kilograms is probably too much propellant that would be feasible, and it only lasted us 9 minutes. So it will likely not be feasible for long flights.
So moving on to our conclusions. As mentioned, we examined the feasibility of multiple concepts and then down selected and did a deep dive on lunar regolith. And as Christian mentioned, we've determined that at this time, lunar regolith is not looking like a fully feasible option for meeting the design requirements, specifically the flight time. We have our hopeful lithium ion batteries would work as a good power source. And our research so far has shown that that is true. And just as a example, we've also looked at pressurized gas and determined that's even less feasible than the lunar regolith would be. So the next steps to finish out this project are to identify the needed parameters for lunar regolith to potentially be feasible for in the future. And then the next steps for this project as a whole, if it's chosen to, research is chosen to continue to be done, will be designing the storage, propulsion, and platform for a drone that would use lunar regolith as a propellant. Thank you. And I guess now we're open for any questions.
All right, thank you, team. Thank you for joining us. So that is definitely an interesting project. You can't use propellers. There's no air, and anything you do exhaust is going to have some consequences.
Yeah, that's correct.
Yeah, so were there any concerns or constraints about using the regolith as a propellant, that it would add more dust to the astronaut or obscure the photos?
Yeah, so we definitely considered that, but since there's no atmosphere on the moon, the likeliness of the dust sort of hanging around in a cloud structure is pretty limited, since they're not suspended in a fluid of any kind. They should settle down pretty readily. As far as the astronauts go, the lunar dust is very sticky, since it has a sort of static charge to it. But the astronauts shouldn't have any problem with that.
I would want to add that I know that typically astronauts can have some of lunar dust on their spacesuits when they're just walking around from the small electric field just above the ground that holds some lunar dust. So it wouldn't be adding more than the amount that they already run into.
Okay, and then I guess if you went to gas cylinders or pressurized gas, you'd have the same sort of effect where it might blow up some dust, but not at much more than they would already be exposed to. Is that correct?
Yeah, that is correct.
Okay, so you think your most feasible design right now is going to be the lunar regolith?
Yeah, really the problem with gas jets is the moon's gravity is just too strong to overcome solely with like a cold gas thruster.
Okay. And I guess you had very few constraints, which was freeing in some ways and probably frustrating in others.
Yeah, yeah, for sure.
Talk about how you tried to narrow down your project topic here.
Well, really, we were focused clearly on the propulsion method. So we knew that we would have no fluid to propel ourselves around in on the moon. So really, we were focused on what is the most efficient way that we can carry mass with us in such a way that allows us to fly for the longest amount of time.
Okay. And then going back to the regolith, how would you either capture, store, and propel that? Have you thought about that?
Yes, we did think about that. So there are a lot of different ways you could do it. We thought of maybe utilizing the charged particle, like the charged property of the dust, and sort of repelling it away from us. We'd also thought about using so we'd use like a highly pressurized tank to be able to push on an area of the regolith and force it out of a nozzle. That way was the one we used for our simulation. And it yielded moderate results. We got about a 10-minute flight time with very, very reasonable geometric and weight values for our drone.
Okay, good. I don't see any more questions online. So let me ask what we've been asking all the teams. It's been a challenging semester with COVID and the winter storm. So what were some of your challenges that you had to overcome and some of your best takeaways?
I I think first of all, the fact that the winter storm took away a week, I know it affected like our whole team pretty much. So taking away that time and then getting back into the swing of things, since we're only a semester long project, you know, a week is a lot of time. And then additionally, with COVID restrictions, we were unable to do any in-person work or secure a lab space or anything on campus to do in-person work if we wanted to try actually accelerating the regolith through a couple methods or any prototyping. And so that was definitely something that we would have liked to do without the current circumstances for sure.
And I would want to comment on another challenge would be just that lunar regolith and its applications are not common or frequent because it's lunar dust, it's only on the moon. And so because of its abrasiveness and its specific properties, there haven't been many applications. There was nothing patented really that could help us. And so I'd say that was probably one of the biggest challenges, is just working with something that has very little properties or very little applications that are proven at the moment.
All right, anybody else? All right, so hopefully in 2024, we'll get a lot more samples brought back that you can experiment with, and maybe you will be working on that. So good work, team. Thank you.
Thank you.
All right, our next team is from Texas A&M University, the 12th astronaut. And let me just make sure people are here. We're a little bit early. So Texas A&M, if you could just keep your videos off during your video playing, and go ahead and rename you if you're not logging in with the same name as you are going by there. So here is their video, and their project is the NASA suits.
Howdy, welcome to the Texas A&M 12th Astronaut Lab. Our project this year is the Scout Augmented Reality Visor design for NASA suits. Our team needs are as follows. Our advisors are Dr. Ana Diaz of the Bioastronautics and Human Performance Lab, Dr. Gregory Chamadoff of the Astrolab, and our NASA advisor is Mr. Darren Welsh.
Background: NASA Suits, spacesuit user interface technologies for students, challenges students to design and create spacesuit information displays within augmented reality (AR) environments. Students must develop an AR user interface that considers the needs of astronauts during the Artemis 2024 lunar landing mission. This includes planning for the extreme environment of the lunar South Pole. For humanity to explore space, we must apply the scientific method to expand our knowledge. The most difficult step is data collection, and it starts by actually getting to the moon and back. The Apollo program cost the US $25.4 billion, averaging $4.2 billion per successful mission. The amount of data collected per dollar is proportional to the efficiency of these EVAs. We can decrease collection time utilizing an AR device that aids the EV crew member in sampling, subsequently increase the number of experiments per mission, and further ensure the safety of the astronaut.
Here is the overview of the Scout AR program. Here are the system requirements for the NASA Suits competition. The user interface shall not permanently impede the astronaut's ability to perform. EVA task instructions shall be displayed. In case of an interruption, the astronaut must be able to continue the task on hand seamlessly. The astronaut shall be able to communicate with ground control at any time. The astronaut must be able to access the status of the spacesuit at any time. Also, a caution and warning system must be implemented to inform the astronaut about a spacesuit anomaly. The astronaut should know its location and how to navigate from one point to another at all times. The user interface shall take field notes for lunar sampling. With these design requirements in mind, our team has developed the Scout UI, which will be explained in more detail in the following slides.
Here's a high-level flow diagram of our design. The controls are powered by a wrist cuff, Mixed Reality Toolkit voice commands, and HoloLens 2 hand gestures. The wrist cuff helps an EV crew member by adding redundancy to the controls. Hand gestures for long 6-hour EVAs may be tiresome for personnel. As you can see, these controls allow the astronaut to access and write important field data, display mission objectives, and increase spatial awareness.
This diagram shows the main features of our design. For the NASA Suits competition, we were asked to work on 4 main tasks involving science sampling, EVA system state, navigation, and auxiliary considerations. All the blocks with darker colors are the features we were able to implement, and the lighter colored blocks are the ones that we'll work on in the future. The main thing to note is that we're using the Telepresence whiteboard along with the Learnerpedia for science sampling, as well as including 3D models and holograms that can be controlled with voice on the HoloLens augmented reality system.
Hi, my name is Ashutosh Mishra, and I'll be presenting the design decision matrix. So in this section, we're going to be comparing 4 different interaction methods: the AR touch, the voice, the gaze, and eye tracking. And we're going to judge it on 3 different criteria and rank it a score between 1 to 10. And then we'll tally up all the scores and then compare to see which is the best interaction method. So going over these 3 different criteria: viability, like how likely is it to implement, how possible it is, how feasible it is, whether or not we can do that thing. Developmental cost, how much will it cost to produce to our design, how much from our budget will it take to build it and implement it into our design. And then finally, ease of use. How easy is it for the user to use the device? How easy is it for the user to become, acquainted with it, learn how to use it, familiarize themselves with it? So based off our results, we figured out that the voice was by far the best interaction method, and the AR touch came in a close second, whereas the gaze and eye tracking were far behind and can be neglected. Thank you. Now on to the next slide.
Hello, my name is Lauren Brady. Here are demos of the features in our Scout UI. We have developed many hologram features that the astronaut and the remote user, either mission control or an intravehicular crew member, can interact with. Seen in the first video is the astronaut interacting with the umbilical interface assembly. The astronaut is seen iterating through the procedure on the UI task panel and flipping the switches indicated. The switch holograms overlaid on the UIA panel animate what switches need to be flipped and show their correct position. Seen in the second video are the interactable box and arrow holograms. These holograms can be placed based on the procedure or by the remote user to indicate position or highlight certain items. For example, this video shows the user dragging the appropriate hologram off the UI panel and placing them into the view of the astronaut. These holograms can be manipulated and placed to indicate specific areas to assist the astronaut. In the future, the Scout AR assistant will be able to suggest and place appropriate holograms to the extravehicular crew member while they are completing an extravehicular activity procedure.
Our hologram compass is a compass that features points of interest set by the EVA or IVA crew. It shows distance and direction from the user to these interest points. This allows an independent astronaut during travel, as he will not need help during this period. The Learnerpedia is our field note journal that uses Azure Speech and Cognitive Services to transcribe the user's speech to text. This allows the user to be hands-free during work. The Learnerpedia also allows for photos and videos to be taken and uploaded for later viewing for other crew or mission control. The first picture shows an attached log, and the second picture below shows a sample photo with a quick description.
The Telepresence whiteboard is a tool used to assist crew members in the field with augmented reality drawings and holograms from a remote user. This use of live visuals allows quicker feedback for tasks and direction, leading to shorter EVA task completion times. In these videos, the HoloLens user's view is on the left, and the view from an IV crew member or mission control is on the right. From a laptop or VR headset, the remote user can see from the point of view of the crew member and provide instruction by drawing 3D splines. In this scenario, mission control is guiding the astronaut towards a waypoint in another room. In addition, the remote user is able to speak with the crew member, monitor the surrounding area, and help maintain complete situational awareness for the duration of the mission. This is all accomplished through a scan environment mesh sent from the HoloLens 2 over the Azure cloud with multi-user replication using the Photon Engine networking library.
Our risk control system is a physical control system for the HoloLens 2 using the Arduino Pro Micro. Signal between the HoloLens 2 and the Arduino is streamed via a Bluetooth module. Our risk control system consists of 3 interactables. 1, a Bluetooth module for panel placement and adjustment. 2, 3 buttons for camera toggle, a main menu toggle, and a solver change toggle. Lastly, we have 2 3-volt batteries that powers the Arduino. The reason we provided our user with a risk control system is so that way they can have an alternative way to interact with our UI that doesn't involve holograms.
Howdy, I'm Kevin Mayorga, and I will be introducing our research section. The main goal for the research team is to conduct research on human factors and to determine its importance to our UI design. The research team has been accomplishing this goal this semester by doing any necessary research for the tech team, such as conducting background research for navigation methods. The other main goal for the research team has been to conduct a study to be submitted in a journal in the future. The study we plan to conduct will test our adaptive navigation system. This system plans to be used to assist in navigation by creating and saving meshes with the HoloLens to serve as landmarks for EVA missions on the Moon. Lastly, the study will test the system in virtual environments such as the one shown of the Sahara Desert in order to test how well the system is able to scan different types of environments.
For our future work, our team plans on continuing studies for our adaptive navigation system. We plan on using virtual data from real environments for our initial tests. We also hope to test the system with the HoloLens in a real-life environment. Finally, we hope to eventually have volunteers to use the system in order to navigate a maze in virtual reality. We also have other projects we plan to work on, such as implementing 3D avatars in our remote telepresence system, testing our software with multiple HoloLens devices, adding a voice assistant with AI, as well as computer vision with deep learning capability. Thank you for watching our video. Do you have any questions? You can contact and check us out both at our website and our social media platforms. Our website is www.12thastronaut.com, and our social media can be seen on Facebook, Twitter, and Instagram at TAMU NASA Suits. Thanks.
Okay, welcome, 12th astronaut. Or should I say howdy?
Howdy.
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 All right, so audience, don't forget, you can go to slido.com to ask your questions. Use the code TSGC to view and upvote other people's questions. So let me just start and ask you how it's going. I know you have a May test with NASA? Tell me about that.
So it's in late May, the second to last week in May. Our original presentation date was actually supposed to be 2 days ago, but it was pushed back to late May. So, but regarding our design, it's going extremely well. We have everything pushed that we need to, and we have all of our technologies and ideas implemented. Now it's just a matter of optimizing everything.
All right, good. And you've got so in your little pew chart, voice was number 1, gesture was number 2, more so than the gaze or the eye tracking. Have you done anything with gaze or eye tracking, or you just left those to the side?
We left them to the side for now. If we have more time, we are thinking of implementing them, but for now we've relied solely on gesture and voice.
Okay. And can a user use either one, like the same controls with voice or gesture?
Yes, sir. So think of it typical iPhone, typical Android. You could just go on your phone, open your application, or you could say, hey, Google, hey, Siri, open Photos, and photos will just pop up. Same thing on our side.
All right, great. All right, questions are starting to come in. How would you apply your design to here on Earth?
Yeah, for this, it can be used a lot in operations, especially in the industry.
So one way it might be used is for guiding someone in a gas plant. If there's a new employee that doesn't know their way around the plant, we could have, with the telepresence whiteboard, holograms showing what switches to press and how to navigate around the different walkways. And that includes having some supervisor watching them and actually guiding them with their voice and drawings in real time. So it could be used anything for that, where anytime if someone needs to be trained on a new environment.
Also, our ability to display interactive holograms and task procedures is very useful for remote assistance, so that someone on a factory floor can get real-time assistance from a supervisor or manager without that person having to take time to suit up and take the safety precautions to enter the factory floor. They can display a 3D model and an interactive hologram and task procedure to guide that person through a maintenance procedure rather than having to take time and show them in person.
Okay, is that the virtual avatar you were mentioning in the video?
Yes, the avatar is the Scout AR assistant. So that's our voice feature. So they can use the AR assistant, or there can be we have pre-programmed tasks in there as well.
Okay, and what does Scout stand for?
It stands for Space Communications Operations and User Telepresence. That's it.
Okay, excellent. Next question here. What was the biggest setback you faced this semester? Of course, we've been in COVID, we've had a winter storm, but in terms of your general project, plus maybe technologically, what were your biggest setbacks?
So I believe our biggest setback was because of COVID, everyone's spaced out and there's only one person with the HoloLens, which is me. So whenever people are designing their programs and whatnot, they can't really see what it's like in the HoloLens. I have to be with them and show them virtually how it's like. The other setback would be probably telepresence whiteboard related. Took a while to get Photon and everything working. So, but that was it. So.
Yeah, and I can explain more about that. It's mainly related to the situational awareness aspects of the remote user, because we have this 3D scanned mesh from the HoloLens that we're sending over the network, but actually aligning that correctly with their drawings, so that we actually know that we're drawing or guiding them to the right place in the real world. It's kind of hard to align the virtual world with the real world while we're far away, and so we worked a lot on getting that calibration set up correctly.
Okay, and what are some of your best takeaways? I know you are all different majors. You've got different engineerings, biomedical. So each of you must have taken something different away from this. And go.
Sorry. Yeah, so biggest takeaway is just the development process. So developing not only yes, learning to develop an actual application and prototype from a distance is one thing, but just that whole idea of saying we're going to have this feature, and XYZ feature done by this Saturday, and then we're going to take Monday, Tuesday to implement it, and doing that process on a weekly basis while still taking into account setbacks or other things like that. I think that's my biggest takeaway personally.
Yeah, for me, the biggest takeaway was a lesson in systems engineering. Since we all have diverse backgrounds and we were working on both hardware and software, figuring out how to assign the team members to the correct task and combine our things at the end of the semester was difficult, because we have some pieces of software that people are working on. It's all just been virtual. And then we have the physical HoloLens and Arduino and everything that we want to connect. And it's a little bit hard to connect software that someone else has written to some piece of hardware you're working on if you can only have Zoom calls. And so a lesson in integration I learned.
I've learned a lot more about human factors engineering and human factor studies, figure out how the system itself relates now more towards humans and how to better integrate the two ideas together of how the system interacts and then how a human perceives the system with this whole project going on. So it's been really fun to do that. I think it's going to get me really ready for my master's program.
All right. Well, thank you very much, team. This was a great wrap up to our showcase. Thank you for joining us and good luck with your testing.
Thank you for having us, and thank you,
Thank you, sir.
Thank you.
All right, to everybody out there on YouTube, as well as our Zoom webinar, this is the end. I want to thank all of the faculty advisors and NASA mentors and all those people that helped collaborate with our teams. You are much appreciated. All the teams, students and faculty and advisors were sent information about judging the posters and the videos that the teams have created. So if you could please do that. The judging is open until Sunday. And then on Monday, we'll send you information about announcing that. We'll have a video presentation that Texas Space Grant will have on Monday afternoon, where we will announce the top teams and the scholarship winners. Thank you to the entire audience. I know we have many more people on YouTube. To all the students, I want to thank for Texas Space Grant, Talia Jurgens and Angelica Cruzinga, who have been working tirelessly behind the scenes. And don't forget, the teams have meet and greets from 5 to 6 tonight. So the teams were emailed information about where to get that Zoom information or the link information for a video chat with the team. All the teams that have sent us information that is posted on that spreadsheet. And you can go check out the teams, talk to them more about their projects, and get to know them. All right, thank you very much for watching. This concludes the Spring Design Challenge for 2021, and we hope to see you next semester, hopefully in person. Thank you very much.